Jagabandhu,
Hello.
let me start.
You can start, sir.
Yeah, thank you. So he is my presentation visible.
Yes, sir. It will be.
Okay, thank you. Good afternoon to all of you. Welcome back to the third day sessions. In this first session, I'll be giving a brief overview of automatic speech recognition system. Essentially, I may not focus on how to develop an automatic speech recognition system because nearly 50 minutes is a very short time. Alternatively, what I will do is I will give you a bird's view of automatic speech recognition area so that we can see where still there is a lot of scope for us as researcher to contribute. That is the goal of this one. Here for this presentation, I have taken exclusively most of the materials from this presentation slides available from Professor Laurent, which is automatic speech recognition, introduction, current tense, open sense. He gave in 2018. I think it's in the public domain. So I have organized my thoughts in the following way. I'll briefly introduce the field of speech recognition. Then I will highlight some of the trends that are there in the speech recognition area. Then how we were attempting to do speech recognition by using machine learning methods, and how in the last decade or so, especially starting from 2012, and it picked up from 14, 15, 5-6 years, how speech recognition and deep learning has revolutionized the speech recognition field. The core part of speech recognition system is acoustic modeling. So the different approaches for acoustic modeling people have tried out, and what are the challenges in the speech recognition area. So that is all. So I will summarize my presentation. Of course, there is a fundamental distinction between the spoken language versus written language. Many of us come from where our mother tongue or medium of instruction is a language which has both the forms, written form and the spoken form. That is where now we don't realize the uniqueness of the spoken language. Of course, there are pros and cons of that, but there are majority of the languages in the world where there is no written form of that language. But still, we are able to process that language and decipher the information. Shows that we should be able to develop automatic speech recognition systems for the languages where we don't have written script. Only spoken form of the language is there. We should be able to. Anyway, when we come to the automatic speech recognition field, what we are talking about is development of a spoken language processing system. So of course, the next question comes, what are the different information sources present in the spoken language? Message, speaker, language, and other aspects will be there. In the paradigm of speech recognition or automatic speech recognition, we are just focusing on the message part. This point I mentioned earlier. I think the representation learning from the speech is a very hot topic where speech processing community can look into it. Then the pattern processing of speech, even though the terminology of pattern processing is very old, starting from the days of pattern recognition. However, in the perspective of deep learning, how do we treat this pattern processing is also an interesting direction of speech. Okay, and the goal of automatic speech recognition is mimicking the human spoken language processing. If you see the whole history of spoken language processing, which started from by electrical means by early 1960s or so till date, we can say the journey started with some simple template matching. That means to say, during enrollment or training stage, we have created templates for the patterns to be recognized, and then use the template. And during testing also, you generate similar template and do the template matching for the recognition purpose. Alternatively, when I go to end-to-end speech recognition, which we are talking about now, where we are directly giving the raw waveform and getting the spoken words as the output. That is the thing what we are talking about now. So that is the journey that has taken place over last 5-6 decades. Okay, so that is about this. We will go in detail. Of course, if I look into the speech recognition, the technical goal is to recognizing the spoken message. In layman term, we can call it as speech to text conversion. If you consider human speech recognition, how we do is we in our auditory cortex, we recognize the sound patterns. Then with the help of those sequence of sound patterns at the next temporal level, we recognize the word patterns, and then we derive the meaning from phrases and sentences. Also, we are able to provide the selective attention. This is all the way we do it on our cognitive system. Even though we don't know exactly how it happened, that is the study of the cognitive speech processing area, but we are all witness to that. The goal here is in the automatic speech recognition, essentially stops at the second level, that is decoding the word patterns by an automatic system. Deriving meaning or all those things is come under spoken language understanding. And selective attention, though, we are not really paying attention. This is a graph which is important, I think, generated from National Institutes of Standards and Technology, NIST. It gives us a glimpse of the journey that has happened in the speech recognition area. I think this figure is generated long back, 2012 or so. They have shown, starting from 1900 till 2011, how people have tried development of speech recognition system and what are their this one. For example, early 1900s itself, the y-axis is word error rate. They had a very high quality signal. The number of words in the vocabulary maybe 1,000. Then they went for air travel planning kiosk in the speech in 1991 or so. So that which is a 5K vocabulary. Then the people worked on broadcast speech. So see, even though if you see that the very controlled, very good, high quality speech signal you have collected, 1,000 word vocabulary, the equal rate comes less than 4%. But when I go for a different natured signal, for example, air travel planning kiosk, which is not a controlled environment compared to what you are collecting laboratory conditions, again the equal error rate goes up. Then people start working on different methods, and finally the performance. Then they take a much more challenging data set. That is how the whole journey has started. For example, there's a lot of attempts on switchboard corpus data, which is a telephone collected over telephone channels. You can see the word error rate was very high, and still seems to be very high, around 20-30% like that till 2002 or something. Okay, then people NIST started developing meeting speech, where speech collected in meeting rooms, and their equal rate, word error rate seems to be on a very high rate, which humans are able to do it very effortlessly. But these are all the challenges that were there before the era of deep learning came. People were usually, take a style of speech and the environment in which it is collected and focus different challenges to do that. Ideally, if I want a speech recognition system which can recognize the speech signal which is of spontaneous nature, just like what we discuss across table, and we are able to decipher the message, and speech collected from multiple speakers, unlimited vocabulary, any acoustic condition we should. That is the human reference we have. As humans, we are able to do human speech recognition under all these conditions without any much problem. Of course, highly noise condition, then human recognition also may not be, but in most of the practical conditions, we are able to do. But each of them, as you see, suppose if I go for a broadcast speech, the equal rate is around 30 or something. That's too high for compared to the human recognition. That is where the whole automatic speech recognition. As shown in this figure, practically if you see, performance differ greatly for different context. The performance of spontaneous speech is much poor compared to read speech. Performance of large vocabulary speech is much lower compared to the small vocabulary. Performance for noisy case is much poorer compared to the quiet condition. These are all the standard sets. observation that people have made. And before this deep learning era came, most of us were focusing on this condition. Okay, what is the type of, okay, let us focus next few years on developing speech recognition system for conversational speech. That is how somebody started from 97 or so, and that journey continued up to 2004 or 5. Then they started, okay, we'll go for much more challenging. Meeting room data started in 2004, 5. Then it went up to 2010 or 11. So the performance were, essentially all the research groups were focusing on. So what it says is, it was showing a brittleness of automatic systems in building speech recognition system. Vis-a-vis, when I go to human the speech recognition, we have, unless it's a very noisy case, I'm considering that, suppose you are standing in the railway station and the train passes by you, that sound, you will not be able to hear any message from, suppose you are talking over a mobile phone and the train passes. Until the train passes out, you will not be able to make out the message. And unless such noisy conditions are there, in majority of the cases, you are able to make out the message. So without any much difficulty in deciphering the content. Whereas when I go to an automatic speech recognition, each of them becomes a standard issue. That is where the whole effort is happening. But luckily, what happened is, this is shown for a standard English telephony data set. Once this, earlier these were having, so they have taken English telephony data sets from switchboard corpus, which is essentially, if you see the switchboard corpus started collecting from 94 onwards, that data set was used. And she has shown, the author has shown how the performance of different systems, for example, people did some adaptations on the standard GMM, HMM models and achieved some improvement in the word error rate. Then they came up with improving HMM training strategies. They further improved the performance. But the real thing is, 2012 or so, there is a breakthrough happened in terms of demonstrating the significance of deep learning models for building acoustic models and followed by speech recognition. Suddenly, a steep decrease in the performance in the word error rate came. Performance decrease, word error rate decrease. Performance improvement happened accordingly. Initially, it was driven by the impact of deep learning. Then later, it was defined by the complex architectures, like different architectures were coming in terms of attention modeling, transformer modeling, all those things. Those complex architectures further fueled improving the performance of the speech recognition. Just consider English telephone data set from the speech code corpus. Currently, what we have is the performance which is comparable to human level performance. Of course, now the question comes then whether speech recognition is a solved problem. That we will see at a later slide. But what is important to note is, before this deep learning era, 2011 or 12, the decrement in the word error rate was rather slow, and it gave a very steep decrease in the word error rate. Accordingly, significant improvement in the performance in the last 1 decade. That is squarely attributed to the deep learning approach, as well as different complex architectures available in the deep learning. Of course, another thing says, without that one much emphasis, that the large amount of speech data was also available for building the system. So, if I see what has happened in this journey of development of automatic speech recognition, we started with an elusive goal of mimicking the human speech recognition, and accordingly, it has contributed several technological trends. We have a sensing equivalent in terms of microphone, then digitization of the speech, then the whole speech signal processing gave a birth to digital signal processing area for pre-processing and feature extraction. Then came pattern recognition, later version machine learning, now the deep learning. So in the initial days of development of speech recognition system, as I mentioned in the opening remark, we were doing template matching. Template means you develop some fixed dimension vector like thing, or a variable dimension also. One template during training, another template during testing, and try to match them. That is the crude way we were doing, either using vector quantization or dynamic time warping and then do the matching for recognizing the words. From there, the journey, now we are talking about what are called end-to-end systems, where you give raw signal as input, either in terms of time domain waveform or spectrograph representation, spectrotemporal representation, and get the output from the deep learning model in terms of the decoded spoken words. If you see all these things, of course, in this deep learning era, the whole things are merged into one model. But when I go to conventional machine learning area, except into end-to-end, even in the initial systems of ASR using deep learning, we have two parts. One is speech-to-symbol conversion, which is nothing but phoneme recognition system. Then combining the sequence of symbols to word level, spoken word conversion. Okay. Then the word are grouped into phrases or sentences, but mostly we are focusing on these two steps. So what is important to be highlighted at this point is both for these crucial steps. The kernel step is phoneme recognition. Then on top of it, this phoneme to word conversion. Here, when people started developing automatic speech recognition system, they relied heavily on the written form of the language. All the approaches that have been developed are based on the knowledge available from the written form of the language. Of course, it had its own advantages and disadvantages that we will discuss. But if you look from a pros point of view or advantageous point of view, really the written form of the language has aided in building automatic speech recognition systems. But the cons part is, or the limitation part is, if you have a written form of the language, then all this framework that we have developed for automatic speech recognition system will work. But if you have a spoken language, it does not have a written form, then this framework will not be useful. Then we may have to look for an alternative framework, or with all difficulty, we have to mimic this framework to that spoken language also. Okay. If you consider the era of machine learning means, of course, deep learning is also a specialized area of machine learning, where if I don't use the deep learning models, any of the other machine learning models I use, like hidden Markov models, Gaussian mixture model combination, or support vector machine, or the earlier versions of neural networks, to differentiate with reference to the current trend of deep learning, we call them as shallow neural networks, or dynamic time warping, or any of those things which you use, they come under this clustering or something. They come under this bandwidth of machine learning. So here, we used to use speech signal processing for feature extraction. As I explained in the last session, since machine learning do not have much depth like deep learning models, they will not have the capability to process the raw data and do the pattern model. That's why they outsource this feature extraction to domain knowledge based speech signal processing methods. So once I have the features from the speech signal processing method, I use those features and do the pattern modeling by using machine learning techniques. Then from the written language resources, we exploit what is called pronunciation dictionary. Then also we exploit the language model. So both these additional resources that we get from the written form of the language has helped in building the automatic speech recognition system. Significant performance improvement using these written language resources. And so in this process, what happened is, for the languages, major languages like English, Hindi, maybe another scheduled languages of India, or French, Spanish, where when we treat them as major languages having written form resources, we became very comfortable in using the dictionary and language model. As a result of that, we did not pay much attention to the better modeling of information that is present in the speech signal. Whereas vis-a-vis, if I consider human way of speech recognition, we give a lot of attention, because when I'm doing human speech recognition, I don't think any of the language components will come handy, like pronunciation dictionary. Of course, it can be a spoken language resources we may be using, but may not be the written form of the language. Okay. So in that process, what we have done is, we have not paid much attention to deriving maximum information that is available in the spoken form of the signal. That is evident, suppose compared to earlier speech signal processing method by Mel frequency capsular coefficient, if I look for any other method by using deep learning methods nowadays, it gives much higher phoneme recognition performance, which shows that much more information is available in the speech signal, but we were not paying attention for that. Okay, and once you are lost, once you extract MFCC, you throw away the whole signal, and you lost the information. So as a result of that, whatever you struggle to do, you may not achieve the greater performance. That is where the plateau has come in the GMM-HMM system. And now, as a rater, once you get these deep learning models, the better modeling of information present in the acoustic signal has pushed the performance up by the speech recognition system. That is, if I go by speech recognition using the deep learning models, of course, initial trends were using, again, like a traditional machine learning approach, use speech signal processing for feature extraction, then use deep learning for pattern modeling. Okay. Then they found that the features that you are extracting and using it in a machine learning approach may not be very good for deep learning framework. Then they made those features much more rudimentary. For example, instead of using Mel frequency capsular coefficient, you go one level lower in the feature extraction, that is Mel filter bank energies. The filter bank energies in place of Mel frequency capsular coefficient seem to have given better performance. Then they went one level down. Why do I use any feature representation? Let me give the raw data as the input to the deep learning model. That is where the deep learning models were used for feature extraction. And that is where the concept representation learning came. This resulted in what we call end-to-end modeling. Starting from the raw data, you are able to get the decoded words. Okay, so that is what is the case of deep learning models. Then, if we see in the deep learning for feature extraction, say I use convolution neural network, I have restricted Boltzmann machine, that is deep belief networks for extracting the features. More emphasis was placed on better modeling of information from the speech signal. The fact that you are exposing the deep learning model to the raw data, you have given a lot of opportunity for this nonlinear processing to extract as much information as possible and get the nonlinearly processed features. Okay, and also, as I showed in that figure, powerful deep learning architectures have come. That also has helped in realizing this goal to an extent. Of course, if you come for asking a question, what is involved in speech recognition system development? We need a speech database for that spoken language. We need word level transcription, go by the traditional framework. Then phone level transcriptions are required. Of course, now there are automated ways of deriving this phone level transcription. Then once you have these three resources, we can develop first level phoneme recognition system, then use this phoneme recognition system for word decoding using dictionary. Okay, then phrase or sentence correction using grammar knowledge. So these are the standard flow chart of developing any speech recognition system, assuming that we are following the traditional framework of written form of the language and its resources are available. Suppose if your language has only spoken form, then one way is you have to artificially create all this written form like language and then use this framework. Okay, that becomes very difficult when I go for low resource or zero resource language that we will see. Of course, feature extraction, I have mentioned earlier this one. We don't have to worry too much. Feature is a representation of this emphasized information at reduced data rate. Coming to the pattern, it is nothing but either it can be a distribution information or a sequence knowledge. Earlier, we used to do linear feature extraction by traditional signal processing methods. Now we are doing nonlinear feature extraction or representation learning by deep learning model. Then pattern discovery by distribution modeling, and also pattern discovery by sequence modeling. Then this I have emphasized, I will quickly keep. Feature extraction by short-term processing we used to do in the handcrafted version, where I use either capsular coefficient or linear prediction based capsular coefficients we used to. Whereas when I go for representation learning, that bypasses the handcrafted feature extraction. So feature extraction becomes part of the acoustic modeling and training. The convolution layers in the first stages of the neural network pipeline, deep neural network pipeline, will enable representation learning or nonlinear feature extraction. If you see, in a pictorial sense, an automatic speech recognition system development, where assuming that written form of the language is available, I have the speech corpus corresponding text transcriptions for that. Text transcription means it is sequence of words corresponding to the sequence of spoken words present in the speech. Then, using this text corpus, I can develop lexicon, okay, which is essentially a pronunciation dictionary like thing. Then I can have a language model, n-gram language model, essentially telling the what the possible ways of word sequences possible. And then with the help of the speech corpus, I can train hidden Markov models. Okay. So with the help of this hidden Markov model, I can develop acoustic models or phoneme models. Then during language model, I developed pronunciation model I have developed. Then acoustic model. These three models are to be developed. Then use all these models which are developed during training. So you can see that if I have speech corpus, I can only develop acoustic models. But if I want to put into use for speech transcription, from the text corpus, I should be able to develop other two models. One is the pronunciation model, other is the language model. When all these three are there, I can use them for decoding during testing. So during testing, I get the speech signal, do the pre-processing, then the feature extraction, following the same feature extraction stage, what we have done in the training. Once I have the features, I want to decode the sound unit information and then combine those sequence of sound units to get the word level information by using all these models. Acoustic models with pronunciation, acoustic model, pronunciation model, I get the phoneme sequence, then use the language model to get the word correct, do the error correction and get the word level sequence of it. So this is a very standard framework which we use in any traditional speech recognition system development based on the assumption that we have both spoken and written form of the language available. Just to give a feel how the deep learning has pushed the boundary of speech recognition, this is a very landmark paper came in 2012, produced by Professor Intel from University of Toronto and other groups across North America, that they have demonstrated successfully the usefulness of deep neural networks for acoustic modeling and speech recognition. The shared view of four research groups, four independent research groups, independently carried out the development of the acoustic modeling or phoneme recognition system, and they reinforced the findings from others. For example, before this deep neural networks came, they were using this GMM-HM as a standard model for acoustic modeling, phoneme recognition system. And the phone error rate that was coming there was around 27.3%. Nothing needs to be attributed to that number. Just for comparison, I'm reading out that number. On a standard TIMID database. TIMID database is a very high quality speech database. But since it has been prepared about 30, 40 years back with a lot of care and less errors, it has become a gold standard database. Even though it is a few hours only, it has become a gold standard database for evaluating phoneme recognition systems and speech recognition systems. So on the TIMID database, they found that about 27.3% error was coming. Any amount of people do around taking GMM-HM as the model for acoustic modeling, and a lot of research activities were happening in terms of changing the feature set and doing the adaptation. So many things they did, but the performance was hovering around 27.3 only. Okay. Then when these groups independently explored, the first thing they told was the initial version of deep neural network model, which trained in a traditional framework, which used a randomly initialized weight, it gave a performance of about 23.4%. You may say, oh, what is the big deal from 27 to 23? It is a big deal because an absolute improvement of 4% was not possible so easily because it was hovering around 27.31. It caught the attention of that. Okay. So here what they did was the deep neural network with randomly initialized weights and using standard handcrafted features, it gave a significant improvement in the performance. So which shows that I have replaced the machine learning model of GMM HMM for acoustic model with a deep feed-forward neural network with randomly initialized weights. So that gave this much improvement in the performance. Then they felt instead of randomly initializing the weights, can I have a better strategy for initializing the weights? That is where this combo of deep belief networks and deep neural network gave, which further improved the performance by about 1%, which shows, again, if you, instead of randomly initializing the weights of the deep neural network, if you have a better strategy for pre-training the weights so that they don't start from a random space, because in a deep neural network, you may aware about the vanishing gradient problem. So vanishing gradient or exploding gradient. As a result of that, many of the weights in the initial hidden layers may not be adopted well. So even after training, that's why this deep belief network will give us an opportunity to greedy layer-wise training of the deep neural network. Hence, weights are better exposed to the actual data. So hence it improved. Then again, they replaced, DBM, deep belief network by convolutional deep network, and also they use filter bank energy rather than MFCC. It gave 20%. You can see from the traditional feature, they go one level lower in terms of discretization. They use directly filter bank energies, which gave 20%. So from 27.3 to 20% was a big jump, which caught the attention of the whole speech processing community. Of course, never looking back from that angle. So now you can see when I go to this GMM, HMM to DNNs, one is the model complexity has improved. Instead of using the GMM, HMM, I'm using deep neural network. Further, I have rudimentarized the features, which is a low level features are used. In spite of that, it gives, what it shows is I'm trying to do a better modeling of the information from the acoustic signal, because phoneme recognition is only playing at the acoustic signal level. So this improvement, 7% improvement, the question now is how does it scale to word error rate or something for developing the speech recognition system. For that, they also conducted the speech recognition system. Suppose if they had a GMM, HMM acoustic unit, acoustic modeling based speech recognition system, where additionally, once you decode the phoneme sequence, you use the language model and it's fun pronunciation rules for correcting and combining to form the spoken words. It gave a word error rate of about 23% on a one data set called Hub data set, and 27.4 on rich transcription data set. Of course, this cannot be compared with timid database. This timid database, only this slide we have to compare, 27 to 20%. Then coming to the GMM, HMM, here two data set. This will be compared with the second row. For example, word error rate for the same data set, Hub data set, instead of 23.3, it came down to 16.1 when I used DNN-based system for acoustic modeling. Okay. Again, the rich transcription 27, it came to 80, which shows whatever better modeling you are doing at the acoustic model level, that indeed gave the same trend, improvement in the word error rate. Otherwise, the other framework of using the language model and pronunciation model, that did not change. The framework remained same. Only the better modeling of the acoustic signal information that resulted in the improvement in the speech recognition system. Okay. Of course, when I see the acoustic modeling using hidden Markov model or GMM system, complex sequential patterns of the speech are decomposed into piecewise stationary segments. Then sequential structure of the data described by a sequence of states. That is the basic working principle of hidden Markov models. So the hidden Markov model essentially modeled the transitions from one acoustic feature vector to the acoustic to capture the sequence knowledge, whereas the local characteristics of the data by the distribution of those feature vectors in terms of GMM observations. So in that way, if I consider a hidden Markov model, the state distributions are done by Gaussian mixture model, whereas the transition from one state to the other state were done by the hidden Markov. That was a very standard modeling technique before this deep learning model came into picture. Of course, late 80s and early 90s, people started using the shallow neural network as an alternative to hidden Markov model, GMM Kumbo. But what they saw was the performance, the neural network's training was much slower, and the performance was much poorer compared to HMM GMM combination. Okay. However, for example, if I go for HMM GMM model system, we assume a specific nature of the distribution of the data points within the state. But the advantage of neural network modeling was there was no assumption about a specific type of data distribution. That was the advantage. However, it was very slow in training compared to HMM, and it was not scaling to larger tasks. So as a result of that, the GMM-HMM combination remains unchallenged. So the interest in the neural networks also went down. The only take-home learning from the neural network architecture at that point of time was they felt the state modeling that we were using by GMM models, in place of that, if I learn the distribution from a neural network and use that treat the output of the neural network as state distributions and use that knowledge in these states, that framework seemed to be working slightly better compared to standard neural network approach for phoneme recognition. So this is one of the connectionist approach for speech recognition, they say. This is one of the remembering milestone contributions in shallow neural network area. Essentially, the state distributions are modeled by the neural networks and use that knowledge in the states of the HMM and then decode to get the performance. Of course, this architecture was used in the later DNN era also. This image shows DNN, but the framework itself was proposed during the shallow neural network area. Even with this performance was comparable to that of the GMM-HMM. It was not much superior compared to GMM-HMM. Only advantage was we were not making any assumption about the actual state distribution. So that was the advantage of that's one. Now, so these were the things. Coming to the deep learning breakthrough that happened in 2012 onwards, one of the qualities attributed for that was, like in computer vision, like ImageNet task or something, object recognition you might have heard, that is where the deep learning breakthrough, convolutional network breakthrough came much earlier compared to the speech processing area. Like in that vision, the breakthrough came because of the more amount of image data in terms of ImageNet available, becoming a large availability. Then they tried convolutional network. You might have heard about some AlexaNet and some other standard networks. That gave a significant improvement. Same thing here also. In 2015, there was an English Libri speech database of 1,000 hours. Okay. Earlier, before that, now people are talking about timid database. If you consider it is less than 10 hours. On any other data set, no, it is in terms of 50 hours, 100 hours or so. For the first time, Libri speech was released publicly available, 1,000 hours of data in English. And this people used for building speech recognition system. And they showed that when I use this 1,000 hours of data, the performance of the DNN system improves. Then came in 2016 by Baidu, they developed deep speech 2 models, where again, English language, 12,000 hours of speech data was made available. Then came Google. They released 18,000 hours of data. Then they released more than 1 lakh hour of data. You can see the amount of speech digital data available grew exponentially in a short span of 5-6 years. And this was one of the factors which drove complex architectures, availability of large amount of speech data in English, drove the significant improvement in the performance. Of course, you need a lot of computing infrastructure. Thanks to the availability of the GPU, we're able to crunch those large amount of data. And of course, better optimization algorithm training objectives came. And there are ASR toolkits to help in dealing with these deep learning models like Kaldi toolkit, TensorFlow, and the like. These are all helped to push the boundaries of development of speech recognition system for English. So that is where all that. Suppose if I go for this more than 1 lakh hours of speech data, the performance of the English systems is very good in a practical setting. Now the question comes is, okay, if that is the case, is there anything left in the speech recognition area? That is the question we have to ask. So once I have 1 lakh hour of data, whether speech recognition is a solved problem or not. For this, there are some case studies here. If you look into the challenges in the automatic speech recognition system, where we have still a lot of work to do. If I go for different case studies, suppose if I consider case 1, where we have used a Wall Street Journal data set, automatic speech recognition system, a quoted performance in this paper, gave an equal error rate of 3.6%. Whereas human speech recognition for the same data set reported here gave a word error rate of 3.6%. Here it gave a word error rate of 5%. What it says is the automatic speech recognition system performance is even better than human speech recognition system performance. So naturally, we get an doubt that is automatic speech recognition solved problem. Not the case. Suppose let us go to the next case, case 2. Another standard data set, Watts-Forge data set. ASR system gave a performance of more practical set at 7.5%, whereas human speech recognition system gave 4.85%. That means to say, depending on the quality of the data, the performance of the ASR system changes. Similarly, when I go for much more, relatively more noisier data compared to the previous edition of Watts-Forge, ASR system gave 22.4%, HSR system, human speech recognition, also gives 22%. Of course, comparable, but 22 is that means to say every 100 words, about 22 words are wrong. That is not acceptable for it. For example, human anywhere less than 5% is acceptable for practical purposes, application side. But here in the noisy case, the performance is more. Still improvements are needed in ASR. That is another direction of looking into. Of course, they went ahead and collected very noisy cases, both realistic noise conditions as well as simulated noise conditions. The ASR system performance, even deep learning models, fell down to 45% word error rate, whereas human speech recognition also was equally difficult. It came to 31%. But you can see that human speech recognition is still relatively better compared to automatic speech recognition. But what it says is a lot of improvements are needed to deal with noisy data. So whether a cognitive, so that is where the relatively better performance by human speech recognition system shows that our cognitive system, which is the core of our human speech recognition, seem to be performing, giving more robustness under noisy conditions. That is where, as I mentioned in the first session, the invariant representations that may be exploited in our cognitive system, whether there is any clue we can get from the cognitive speech processing to deal with the noisy condition data. So that is where a lot of research direction happens. Okay, the take-home message in different setups is truly the performance depends on the amount of data available and the complex structure you are using in the deep learning model. and the conditions on which the data is collected. So that is one part, practical, different challenging conditions. Second thing is coming to the languages. If you see any of the attempts by major companies and so on, their focus is mainly on the major scheduled languages. Of course, this number is not to be taken with so much accuracy, but it is true that there are several thousands of spoken languages in the world where out of that only we have taken a very, very small minuscule set, maybe 100 spoken languages, and we are trying to develop ASR system. In that, for example, if I take English, which has more than 1 lakh hour of digital speech is available, I am claiming it is working good. But what about the other language, 5,900 languages? Okay, what is involved in developing ASR system for these languages? And this question is very relevant for our Indian languages. Of course, now for some of the scheduled languages, we have started getting some more data, but still a long way to go for many of the Indian spoken languages to develop speech recognition system. And it is also shown in some of the challenges that if they consider low resource languages, okay, that means to say the amount of transcribed data available is less, and dictionary things are relatively less accurate, all those things. The word error rate is around 50%, even using the end-to-end models. Okay, so that shows that different strategies are needed to deal with low resource conditions. See, I cannot say for this low resource language, I will also collect 1 lakh hours of speech data and then word error rate less than 5%. That is not a scalable framework. That is where we can think of coming up with frameworks for development of speech recognition system for low resource languages. And there are languages where there are zero resources. Okay, unknown language, unannotated raw speech is available. I don't have any other resource, no transcribed data, nothing. Even I don't have knowledge about that language also. Can I, with all these latest complex deep learning models available, can I discover invariant subword units, that is the phone units that are there? Or is it possible to discover the spoken words in that? Or can we build useful speech technologies without any textual resources? That is the question we are asking. You can see when I go for low resource, at least speech data had some transcriptions available, but there is nothing here, textual, purely spoken language. So that is where people are nowadays talking about next big challenges for deep learning models. Can we build algorithms that learn languages like infants do? Can we build algorithms that extract meaningful units from unknown languages? That is pattern, automatic discovery of the sound units present in this one. Of course, this is a very, very relevant thing for our Indian context. How to develop speech recognition system, automatic speech recognition, multilingual scenario. This may not be very relevant for when you go to countries, advanced countries where they mostly use 1 or 2 languages. A country like India, we speak at least 2-3 languages when you use 2-3 spoken languages words in a conversation. So how do I develop an automatic speech recognition system for a multilingual scenario? There are frameworks earlier where you treat it as a combination of several unimodal or unilingual ASR systems, but recent end-to-end speech recognition system where it has clubbed acoustic, pronunciation and language models are integrated into a single neural network. This framework can be exploited for developing multilingual ASR system. So that is another challenging direction where we can focus for ASR systems. Even there are many other ancillary things like can we leverage on these multiple sensors to design noise robust approaches? Okay, and can we focus on to describe what these neural networks, deep neural networks are learning? Okay, of course there are new concepts in deep learning like adversarial examples to improve the overall robustness. Can we analyze the biases between genders, dialects, regional accents? Okay. Or again, we have a very interesting problem in Indian scenario. We do code switching from one language to the other language. How to develop multilingual ASR for such a system. So these are all some challenges which are there. What it says is, when I see the performance in the ASR system, um, performance in the ASR system, uh, uh, only for selected few languages of the world, the performance seems to be comparable to that of humans under certain standard operating conditions. Of course, there are practical operating conditions, but in majority of the other cases, still there are many challenges. Thanks to the way of collecting, possibility of collecting relatively good amount of data, even though not in terms of that type what we are collecting for English, but we can collect reasonably good amount of data even for low resource and zero resource languages. We can focus on developing speech recognition. We have enough research problems to work along. Of course, in many stages, like better modeling of information, we may be able to exploit some of the concepts in the deep learning, especially the noisy phenomenon. How do I handle this cognitive speech process? I think with that, I will stop here. If you have any questions, I'll be very happy to take. Any of you? Of information available. Okay. Ultimately, so what it says is, as human cognitive system as a reference, if I assume that I have a miracle module available, which takes me the raw data as input, just like our human ear takes, and gives me the spoken words as output, the output is available at around 50 bits per second. That means a much lower rate. Okay. So even modeling and decoding strategies, when you are developing ASR frameworks motivated from the cognitive speech processing, says that you don't have to really worry about using that high data rate conditions for building. Even you are allowed to reduce the data rate and try to exploit as you move from one layer of training to the next layer of training. Only thing is, you need to start enhancing the information which is relevant for the speech recognition system. Assume that given a speech signal under whatever noisy condition, I am able to spot the 10 phonemes I am going to get per second. I think that is more than sufficient. But of course, it's an elusive goal to go. Only some small confidence this cognitive speech processing gives is, I don't have to, we used to think from a signal processing point of view, 8 kilohertz speech signal with 64 kilobits per second. We have lost a lot of information. I go to 16 kilohertz where I have 8,000 hertz as the speech signal. That gives much better performance. So we don't have to look from that angle, because the information that is to be decoded is at a much lower rate. But of course, current strategies are by signal processing we are unable to do. That is where your spectrotemporal representation you go. Even though the original speech signal may be at higher data rate, if I look visual representation of the information available, that will be at much lower rate. So that is the, I hope I try to clarify your thing. What I want to say is, we need not blindly take this concept of lower data rate. What it says is, you can get representations which are operating at in a sparse and much lower rate, but however, distinguishing features are available to mark the phonemes. That is more than sufficient to get a robust speech recognition system. So that is what I want.
Okay, sir. Thank you.
Thank you. Any more questions? Okay, if there are no more questions, let me stop hearing. Thank you very much. Professor Rufina, maybe another 2-3 minutes.
Okay,
Let us start at 3 p.m.
it's okay. Thank you.
Hello. Yeah, Professor Rufina, you can start now.
Okay, thank you. I will share my screen now. Well, good afternoon for all of you. I hope during the last session of the course I can see your faces because now it's like talking to the monitor, but I think that we can discuss all this stuff together in the last session so I can see your faces. I begin with the lecture 6 of this course. Here I will talk about intelligent and varied speech processing and recognition also. I think that the talk of Professor Prasanna gives us an idea of all the effort of the research community in order to solve this complex problem of speech recognition. So we try to see how the human auditory system and cortical and brain system do this complex task. Well, speech recognition, as we So now it's really a complex and difficult task, even more than I think 30 years of research was needed in order to get results in some tasks similar to those of humans. So in spite of that things, a human person solve this complex task in naturally and without much effort is really, we don't pay attention of all the processing our brain is doing during hearing or during speech. And we do all this with very good performance, even with noisy environmentals or in difficult conditions. For example, even people with some disabilities can hear, understand well what other person is saying. So this is an impressive performance from our auditory system. We also can interact with other persons and even recognize their emotions. People can be angry, bored, tired, or something different emotional states, and you can understand perfect what he is saying in both in more or of the situations. And even you can recognize if the person is, for example, angry in a conversation, telephone conversation, for example, because he changed or she changed the way he is speaking. Well, he shout or she shouts, for example, and loud is tune on all of that changed completely the way he talk or she talk. But human person can perfectly decode this type of emotion from speech, for example. As we already see in some of these tasks, artificial systems are still far from these natural skills. So we need a little more inspiration about signal processing by our brain, especially, and the rest of the auditory systems. This is what we call cognitive speech processing in this course. So what happens with classical signal processing? Well, it really work with good performance, but other rather unrealistic hypothesis, because some of the classical signal processing methods suppose linearity. If we can sort in, we can think in Fourier transform, classical Fourier transform, that it is a linear transform, and it dominated the field of signal processing during many years. Also stationarity, even though we have non-stationary version of the Fourier transform that it called the short time Fourier transform, even though for each window you also suppose some type of stationarity, and also you sometimes assume second order statistics like Gaussian distributions, Gaussian probability distributions in many of the statistical based methods. And also other type of constraints were imposed for simplicity reasons. For example, Fourier transforms is an orthogonal base or orthogonal transform. And even other more recent transforms like wavelet transform and are in generally orthogonal. And the other constraint is to have low dimensionality because most of the classical methods use really very low dimensions, like 1 or 200 samples for the vector. But if we now think it in the how our brain process signals, this type of signal, sound signal, for example, it is all the opposite because the processing is non-linear, non-stationary with higher order statistics. Sure, in non-orthogonally, and as we will see, we have many dimensions in the feature vector that we use in order to analyze and process and recognize, for example, sounds. So the idea is to get more intelligent and bioinspired signal processing techniques with some of these characteristics. First, this type of signal processing techniques have to take into account an automatic selection of the relevant information in the features. This is done by our brain in many situations, that you automatically know where is important information for solve some particular task. They also use different type of discriminant information that is useful to differentiate, for example, from one class of signals from another class of signals. And this is even do in a self-learning fashion, because we can think in how we acquire the language. We was exposed when we were childs to all the sounds around us, but especially our mom's or dad's voice. And in all this complex environment, we can discriminate which is the most relevant information in order to traduce the message. Of course, our parents do like masters that they teach us which to look for in the signal, which words are more important and related to some task, for example. But beside this guided stage, all the other is really self-learning. We also have some interesting capabilities of solving problems. So solve the problems without a complete and detailed guide of how to do it. And also an intrinsic robustness, because we can understand the message in a speech, even though you are in a very noisy environment or hard condition. And of course, all of these new techniques have to look more in what our sensorial systems do with this type of signals. This is not new in speech processing, as we saw. Many of the traditional or classical methods really used information about what the auditory pathway would solve this type of problems. But until now, this is only related to the auditory pathways up to the before, I think, the cortex, the auditory cortex, and all the processing at the brain. We can look, for example, in the way some animals solve complex tasks. For example, bats, that they can localize object in three-dimensional space using sounds. That's a very, very important capability that we also have more limited. So we can think about this about 3,000, sorry, 30,000 dimensional space of in the first stage or earlier stages of the processing, and a very, very high dimensional space projection in the auditory cortex. So the way this was, or this is doing in our auditory pathway is very interesting, because only a small amount of neurons fire of they are firing for a particular sound. For example, if you put a pure tone in our ear of a particular frequency, then very, very few neurons will fire in the auditory cortex. Really, there is a tonotopic distributions of the neurons there. So they are detectors of frequency, but each frequency detector is near to the frequency detector of the near frequency. Or there is an space arranged or order by frequency there. Is at least in part of the primary auditory cortex. In other parts, you have more complex behavior. But I think that these type of characteristics are very important to understand how the brain process signals, at least in the earliest stages. So what happens we talk about this tonotopy in the part of the auditory primary cortex, but what happens in other parts, other neurons? Well, some researchers did some experiments with animals like ferrets and monkeys, and they stimulate the ear of these animals with different complex sounds, and then by some type of signal processing, a method called reverse correlation, they can estimate the spectrotemporal pattern of the maximal activation of each one of the neurons. These are intracranial, intra-brain recordings. In the surface of the brain of the animal, you have many electrodes there. So when you put at the input, at the ear of the animal, one of these complex sounds, then you can register the response of each one of the neurons there in the different electrodes. So by this type of processing, you can estimate some patterns, spectrotemporal patterns, that look like this. Here, for example, you have one of these representations. This is like an spectrogram. Here you have frequency in logarithmic scale, and here you have time for each one of them. And these are different responses from different neurons in the auditory cortex. This is for monkeys and things, and in the bottom you have the same experiment or similar, but for ferrets. These are works from Shama, the group of Shama that he was working during a lot of years in this type of problems, and we'll review in some slides forward his model of all the auditory system. So I think that the important core concept here is the one of spectrotemporal receptive field. This is the pattern that causes the maximum activation of one neuron in the auditory cortex, for example. This type of behavior is also appeared in some other sensorial systems, like in the visual system. That really the research go first from the visual system, and then researchers go to the auditory system. Well, beyond the auditory cortex, there are several areas of the rest of the brain with specific functions that are also involved in the speech perception. There are really many functional models for this complex processing. But now in this lecture, we only take into account the information we have until or stopping in the auditory cortex. Then we review in the next lectures what happens here in the other parts of the brain while we are hearing or while we are producing a speech. So let's talk about auditory models. Well, as we just saw, the early auditory system code important information, these acoustic cues, in order to phonetic discrimination, such as the ones we found at the auditory nerve level. There are many studies from the 19th with physiologically experiments to know how all this stuff is working. So Shama and his group proposed a model of processing of the sound carried out in the auditory system. This model is based on psychoacoustic facts found in physiological experiments in mammals. This is not only this is not the only model we have, but I think it's one of the most complex ones, one of the most used and applied models. So we will review this, specifically the Shama model. The complete model consists of two stages. I think this is the interesting part of this model. In the early stage, the model represents the vibrations along the basilar membrane and the corresponding codification at the auditory nerve, obtaining what it called the auditory spectrogram. And then in the second stage, you have the cortical stage. This model moves forward in the representation from the previous stage by decomposing the spectrogram, the auditory spectrogram, in its spectrotemporal modulation content, using this concept of spectrotemporal receptive fields that we have just saw in the previous slide. And this gives us the sparsity characteristic that we found already in the biosensorial systems. Well, here is a schematic of the early stage of the Shama model. Here we have the acoustic signal. This is the filter bank, the first stage of the model, a cochlear filter bank. Then you have the second stage that model the hair cell and all this behavior inside the cochlea. And then the lateral inhibition networks in the auditory nerve and some type of nonlinear processing that we have there in the auditory nerves and the first colliculus and nucleus and all of that in the auditory pathway before the auditory cortex. So this filter bank consists on 128 cochlear filters. And if you use S as the input signal, S of t, the time. Then the output of each one of the cochlear filters in function of t, of temporal, but also the space. This is the space that you go from the base to the apex in the cochlea. So these are distance in the cochlea, inside the basilar membrane. So this is made by a convolution between the signal S, input signal, and each one of the cochlear filters. We are here, this H is the impulse response of each one of the filter at the location X, and each filter has a characteristic frequency associated with that filter and with the position of the filter in the basilar membrane. So from this stage to the next, the model tried to mimic the output of the hair cells, the hair cell potentials. Again, it used a convolution here, but also here the model used this nonlinear compression function that it is here in this block, because the behavior of this type of cilia in the hair cells is nonlinear. By psychoacoustic procedures, you can measure or estimate this type of functions. So you know the approximate form of the function G that make a nonlinear compression in the ionic channels. And then you have here W, that is the leakage represent the leakage in the membrane of the hair cell. It's something like a low pass filter, a linear low pass filter here with this convolution also, a time convolution. So until now we are in this point of the model. And now the lateral inhibition or inhibitory network here was modeled by this equation, where you take the max value, and also you have a half wave rectifying here in this block. This is also some type of behavior in the cilia that they can go from one side, but not they fire in one direction and not in other direction. So this type of behavior is represented in this type of block, like a half wave rectifier. So this is the way the model mimics the behavior of this stage. And finally, the last stage of this early representation consists in an integration of all these signal over short temporal windows to obtain the finally auditory nerve patterns. Again, as a convolution with a time window, a particular time window. So you have at the output the representation like this. Here in this axis, you have the frequency axis. Each one of these are the characteristic frequencies associated with each one of the cochlear filters. It's a nonlinear logarithmic scale here for frequency, like it's really in the auditory system. And then we have time. So this is like a spectrogram, but with some special characteristics that mimics the ones of the auditory pathway. Here you have a comparison. Again, in the bottom you have a speech signal, and the middle a classical spectrogram. And here is the auditory spectrogram. You can see the difference. Most of the characteristics from the classical spectrogram are there, but you can also see some difference that mimics the spatial characteristic of this sensorial pathway. Well, at this point, I have to ask you if someone have any questions about this model. If it is clear, I can go on.
Sir, sir, I have one doubt in this figure.
Yes.
Sir, in this spectrogram, there is one high frequency component which is not present in the topmost figure. Is that because of the axis, y-axis, or it is missing because it is noise and it is not represented in auditory? Yeah.
That's right. That's right. Because it's a particular limitation of the implementation of this model. Because the information in high frequency is comprised in very, very small frequency range. And I think that this model, in this case, this was computed with a model that have, I think, 8 kilohertz from bandwidth there in total, but the high frequencies are compressed there in the upper part of the spectrogram, auditory spectrum. But you're right. It depends on the implementation, really.
Okay.
You can put more focus there if you want, but in this implementation, you have this limitation. Yes, that's right.
Oh, okay. Thank you, sir.
Thank you. So we can go on.
Sir,
Yes.
I have one query.
Yes.
Sir,
Please.
actually, in the previous slide, the auditory spectrogram.
Yes.
Sir, can we tell by looking at the auditory spectrogram, is it possible to have a one-to-one mapping with respect to the sound units in speech?
Yes, because it is all temporal aligned with the speech signal. So in this sentence, yes.
Yeah, because what Nityam, the previous person asked, that particular high frequency sound which is coming may be related to some fricative sound, which is actually absent in that auditory spectrogram. So can we tell any sort of mapping exist, a one-to-one mapping exist between, because that particular sound is not visible. That component is not visible in the.
Yes, it's a problem of the representation only. But if you see carefully, this energy in the high frequency of the S phoneme here is here in the up part of auditory spectrum. But this is really in very small parts. This is an effect of the compression of the frequency range in the high frequencies.
Oh, maybe. Oh, that means that something is there, right? We can see something,
yes.
Right?
I don't know if you can see it here, like.
Okay. That's what. Yeah. Okay. Thank you. Thank you, sir. Yeah.
Thank you. Any other question? Well, Now I go on. So the next stage is the cortical stage. This model is interesting because it also takes into account what happened in the auditory cortex. So again, in the upper here, you have different types of spectrotemporal receptive field from different biological neurons. This is from ferrets, study from Shama uh, from ferrets also. So the idea here is to try to mimic this type of behavior of each neuron in the cortical stage. So instead of using the real ones, this is experimental data, Shama proposed a model for each one of the spectrotemporal receptive fields that is really a multi-scale synthetic spectrotemporal receptive fields. Because thinking about the idea of wavelet transform, that you have several different scales, something like that appears also in the auditory cortex. Because for speech you have, as we saw with Prasanna, different temporal scales. One scale is, for example, the changes inside the phoneme, and then you have changes at the syllable level and at word, and even suprasegmental changes on the intonation and in the envelope of the energy and all of that. There you have different time scales, and in the cortical auditory cortical representation, you also have neurons that respond for different temporal envelopes. So Shama tried to model or mimic this type of behavior. So he proposed, as we will see, a synthetic spectrotemporal receptive fields that work over the auditory spectrogram by bidimensional convolutions. So the idea is that you have one of these functions, bidimensional functions, that in particular detect some type of frequency, spatial frequency, especially in the sense of these auditory representations, frequency and time. So this is also frequency and time. So you can take each one of these and move around all the spectrogram in order to get a bidimensional convolution. So you get this type of representation as the activation for each time for this neuron that has this type of spectroreceptive field. So now we go to the details. Here you have one of these spectrotemporal receptive fields. These are formulated by synthetic bidimensional composition of two wave functions with this type of shapes, like this and like this, from one dimension and the other dimension. This is the formulation of one of the functions and the other functions. They are functions with some oscillations there. So then you can make a composition from these two functions in order to get the spectrotemporal receptive field, the synthetic one. This composition is made by some transformation over the two-dimensional function, in this two-dimensional function. So then you have a complex spectrotemporal receptive field with some particular characteristics, some spatial frequencies, changes of space frequencies related with change in times and changes also in frequency. So you can make a bidimensional convolution in both dimension. X is associated with frequency and time, and you can get as a result something like this. Here is the auditory spectrogram again. Yeah, and this is only some examples of different type of spectrotemporal receptive fields, synthetic ones. So, for example, here you have fast rate and fine scale, fast rate in time and fine scale. So, fast rate of change and fine scale. Perhaps this is small to see here. But the result of the bidimensional convolution with this type of kernel is the one you have here. That is particularly selective or tuned for this type of behavior here. This type of signals that is here you have formant, but they are formant that are almost horizontal in this representation. Here you have another type of slow rate and fine scale. This is all fine scale representations, but they change in some characteristics. So here you can look for different aspects, different behaviors in the auditory spectrogram. It's like this is a characteristic detector. So it looks for special parts or special features inside this auditory spectrum. This is the way that this type of representation mimics the behavior in the auditory cortical representation. So in the same way, the same fashion, here you have a coarse scale. You can look here that you have a broad representation of time events here and here, like in another temporal scale. So the other interesting thing of this model is that you can download a MATLAB toolbox in the SHAMA homepage, and you can play with some sounds, speech sounds, and try to look what type of representation you get. Any other question about this stage? Well, we go on. The other important issue here is the sparsity of the representation at the cortical level, as we have just talked. So we now we try to look for some recent techniques. We review some recent techniques that can use this type of characteristic or generate representation with this type of characteristics. But why we need this sparsity? For of course is by inspired, but we have to review why this is an important characteristic. Well, by definition, a sparse code is one that represents the information in terms of small number of descriptors, but taken from a large set. Because if you have a small dimension like the traditional method, it's difficult really to produce a sparse code. So we have to make a representation in terms of a high dimensional space in order to get only few of that coefficient in the representation are active for a particular, for example, sound or something like that. There is an analogy of MALAT that you can try to describe a particular concept or animation. Suppose you are looking to a picture and you have to write a sentence describing the picture. So you can use either a small or a large dictionary in order to make two different descriptions. In the in the small in the small dictionary, you have only a small quantity of words, very broad descriptions of concepts. And in the large dictionary, you have more specific words for the concepts, and much more. So the idea here is, with the small dictionary, you have to use almost all the words there. And in the large dictionary, you can select some of the specific words in order to describe better, and only with few of them, the image or the concept you are trying to describe. So here in the bottom of this slide, you can say an analogy, this analogy in terms of signals. Here you have one signal. This is a synthetic signal. You have you synthesize this signal by means of add one pure tone, one delta here, and a Gabor atom here that is located specifically in time and frequency, particular time and frequency. So really, this was synthesized by a very large dictionary of wavelet packet functions. In this dictionary, where you have something like 5,000 waveforms, they are waveforms very tuned for a specific frequencies, like near pure tones, and also near deltas in time, very concentrated in time, and also some intermediate behavior also in the waveforms. So you can select only four, I think, 4 or 5 of these waveforms in order to synthesize this artificial signal. But if you try to make a classical analysis, like Fourier analysis, and you can represent with this dictionary, this is only the real part of each one of the pure sinusoidal waveforms, but it's only for illustrative purposes. But here you have the magnitude of the coefficients. In this small dictionary, you have only 200 and I think 55 coefficients. And this is the energy or the magnitude of the coefficients. As you can see, all the coefficients are different from 0 here. And the information from frequency and time and all mixed, it's all mixed there. So here you can see this peak that is associated with the pure tone. Here you have some information associated with the Gabor atom, and the rest is associated to the delta. But you lose all the time location in this type of analysis. So you can see with this example that using a small dimensional representation is not always the best choice. It is better to have many different type of functions in order to describe very precisely this type of characteristic of this particular signal. Do you understand this analogy?
Yes, sir.
Okay. Then sparse coding has several advantages over other alternatives. Of course, this is bioinspired, as we saw. But they are also optimal in terms of information theory and signal compression also, because the codes, sparse coding produce codes with low entropy. So they are optimal in terms of information theory, as we can see. Here in this table, you have a summary of the different characteristics, principal characteristics of the different type of coding. Sparse coding really is in the middle between local codes and dense code. Local code, you have only one of the elements of the code that is activated per time, only one. This is a local representation. Sparse, you have some of them, few of them that are activated, but only the very, very little with a big amount of activation. And in the other way, dense codes are almost every element are real activated. So in the classic approach, you generally have this type of code or something between these two types. But as you can see here, for example, in the representation capacity, the local codes are very low, very low capacity of representation because you have only one active element per signal, for example. In sparse, it's very high, and in dense codes are even very high, even higher. In terms of memory capacity, local codes are limited, then sparse are high, and dense are low, really. From the point of view of interpretability, local codes is very easy because only one of the elements associated, for example, for one class, it is activated for a particular signal. In the case of sparse representation, a few of them, but that's have a very, very direct relation with the characteristics of the stimulus or the signal that it represents. And in the case of dense codes, as we already saw, it is very difficult to, or more difficult to interpret the characteristics of the signal seeing the code. And then you have another interesting properties like the generalization capability. If you train some type of classifier with signal or vectors with these coding strategies, then you get non-generalization capability for local codes and good for sparse and dense code. And even robustness, this is important. Local characteristics, they are really not robust because if you put some noise there, then you lost all the characteristic of the representation. In the sparse case, this is really high because you have only few of the components are with high values, and all the other are with low values. So you can, for example, put there a threshold and only keep the coefficients or the elements below. You threw out all the coefficients below that threshold, and then you keep the more important information. And also dense codes have some robust capability, but it depends on the situation. So if you see this summary, sparse coding really have many advantages over the other alternatives. So in this slide, I want to show you how it looks, the different codes of the different type of vectors you get from different type of codification strategies. Here in the upper side of this image, you can see the canonical representation and the normalized histogram is go vertical in this direction in order to see more easy the meaning of each of these type of histograms. It's like you estimate the probability density function of this random vector. So in this case, you have only one. Really, for this example, I also put a very, very small value in another part of the vector in order to get this type of histogram. But almost all the values are around 0. Only one, this element at the 10 location is different from 0. So you can not see here because it's very, very small, and so it can't be seen in the histogram, but it is there. And then in the middle you have sparse code. As you can see, only 3 of them are really with high values, and you have other activation but with little values. So this is the type of probability density functions that you find in this type of coding. There is all higher order. You have to use higher order statistic in order to describe this type of representation, like Laplacian, for example, Laplacian probability density functions. And then in the bottom, you have a sparse encoding alternative, where all the elements in the code are active. And so you have something like a Gaussian probability density function. So I think that with this image, you can make an idea of the different properties of each one of the representations. So let's talk now about the difference between sparse and independent codes, because both characteristics are important. Sparse, as we just described, is the description of a signal in terms of only a few significant features. But in the independent codes, the features or causes are assumed to be also statistically independent. So both criteria are different, but they produce representations with similar properties, and both criteria can be applied simultaneously, as we will see in what follows. And this is interesting because when you use both criteria, you can interpret every element of the codes in terms of the detection of meaningful characteristics from the particular signal you are trying to represent with this type of code. So now we proceed to present the sparse signal representation using discrete dictionaries. That's the technique we will describe. So a dictionary is really a collection of signals that they call atoms. This collection of signals is arranged in a matrix whose columns are the atoms. So a sparse representation of a signal S based on a particular dictionary that we call phi here consists in finding appropriate linear combination of the atoms in the prescribed dictionary using only a few of them. This is the sparse representation. I have to make a remark here that this type of representation is linear in the synthesis way, but non-linear in the analysis way. So this is an important remark. We can talk again later. And the problem of finding this appropriate representation can be divided in two different subproblems. The representation or inference problem, here you have the dictionary and you want to have or estimate the representation. And the other problem is the dictionary learning problem. You have some signals there, and you want to find the optimal dictionary that you can use to represent better this collection of signals. So now we proceed to describe each of these problems and the possible solutions in order to get sparse representations. So the first idea here is that you can use this as a generative model. This type of model, you have the dictionary here with n rows and m columns. We suppose a fixed dictionary. And then the idea is you can generate this random vector of coefficients, activating only few of the elements in the vector. So when you push this button, then you generate a particular signal with random coefficients here. If you push the button again, you generate another random coefficient, and you can generate another signal. So the idea here, well, the signals are in this space of n dimension. It's an n-dimensional signal. This is the generated signal. P is the matrix of the dictionary. Usually M is more or greater than N. You have more columns that rows in the dictionary. And also each phi that say here is each of the atoms of the columns of the dictionary. So we want to use these atoms in order to represent the signal in this way. So this is the synthesis model. If you multiply P per A, you have S, the signal. You can sometimes you can have some noise here. That's the idea. You have here approximate value of the representation, and the vector A is the vector of the representation of the signal. So a sparse solution of this problem is to find this A vector which has a few non-zero components, like the quantity Q. This is we said that L0, the zero norm of the coefficient A, is Q. And a way to obtain such a sparse representation of S based on the dictionary consists of solving the following optimization problem, where the optimal A is the argument that minimizes the zero norm of A, but subject to the linear generation model, that S is equal to phi per A. So here, this denotes the L0 pseudo-norm as defined as the number of non-zero elements of A. But solving this problem is generally an NP-hard problem. So to overcome this issue, several relaxed versions have been considered by different researchers. So we will review some of them. For example, Chen and collaborators proposed a convex approach to simplify the inference problem called basic pursuit. Here, the reference is missing, sorry. So instead of minimizing this norm, the zero pseudo norm, you minimize the norm 1. Norm 1 is really this problem is more easy because it is a convex version of the previous one. And this problem can be converted into a traditional linear programming problem, which is very, very easy to solve using some of the linear programming techniques. So here in the bottom side of the slide, you can see which is the convexification that they are using, that Chen proposed in his work. So here you have a representation of a two-dimensional codes. Here, this type of curves are isonorm curves. Isonorm curves. So as you can see, you have this type of shape here in the you can see L0 norm space. And the idea here is that you have to find the less value of the norm, of the L0 norm, that permits you to represent the signal with the linear model that is in this very low dimensional space, is this straight line here. So the idea is that if you use, instead of zero norm, you used one norm, then the solution is really near the other solution. And this type of problem is best solved with traditional linear programming method. So this is the idea for basis pursuit. But then another authors, Marat and Zhang, also proposed a greedy method in order to solve this problem. This is not an exact solution, but in many of the problems it's a very, very good one, and it is more fast than the solution of this convex problem. So the idea is that proposed Malat and Zhang is to start from an initial approximation that we call S0, it equals to 0, and a residual that is equal to the signal. And we will construct a sequence of sparse step-by-step approximation to the signal S. For example, in the step K, this atom at the stage K, you try to find the atom which best correlate with the residual. You can do this by measure the correlation of each one of the atoms with the signal or with the residual that is equal to the signal in the first stage. So then we find this atom with the best correlation, and you add the value of the signal, the approximation of the signal at the previous stage, and the value of the atom, but multiplied by a scalar value. This scalar value that is associated with the coefficient or the value of the correlation between the atom and the signal and the residual. So in this case, here you use an inner dot product there in order to an internal product in order to get the value of this coefficient, and then you subtract from the residual the value of this approximation at this stage. And after m steps, you have a representation with this residual. And for example, you can do 10 steps and you can get 10 coefficients. They are different from 0 in general. So the value of m marks also a lower bound to the sparsity of the representation. This is a really very, very simple approach, but it works very well for some or a vast different signals. Do you understand this procedure?
Yes, sir.
Okay. Well, now let's go to the dictionary learning problem. Here, this is a more difficult problem because you have to find not only the dictionary, but also the coefficient. So you have to simultaneously solve to find the dictionary and also the coefficient for each one of the signals. Because in this problem, you have different signals. You have a collection of signals, S, that all are generated with this particular fixed dictionary that is unknown for you. But you can think again, as we propose in the first slide here, that you have this type of generating model or generative model. So each time you push here, you have a different S signal, and the dictionary is always fixed. Of course, for synthesize all the signals in this artificial experiment, you know the dictionary. So now what you want to do is to plant the inverse problem. The direct problem is to synthesize the signal, and the inverse problem is to get the dictionary from the signals. So this is a complex task. So here, different authors that propose different methods. We, for a question of time, we didn't go in more detail or most details behind this approach, but one of the most used one is KSVD that was proposed by Elad and Aaron in 2006. And also some previous implementation of noise over complete independent component analysis that also using some sparsity constraints on probability density function of the coefficients. They propose also a method in order to find the dictionary. So we will go on. Now I will present you one of my own works that I try to, in this work, I try to mimic some of the characteristics of the auditory cortical representation, but using these sparse representation techniques. Not the model. You can use also the SHAMA model for the cortical stage, but in this work, I try to use these techniques in order to approximate the characteristic of the representation at the cortical level of the auditory cortex. So in this work, we look for getting get a robust representation for phonemes in a phoneme classification problem. This is work with one of my students in 2012. So the idea here is that you compute the dictionary of bidimensional atoms. Of course, each of these bidimensional atoms resembles the spectrotemporal receptive fields of the auditory cortex. So the estimation of the activations using sparse representation mimics the cortical representations. And the idea here is to try which is the performance to a classifier like a multilayer perceptron on phonemes that are representing using this type of technique. And what we demonstrate here is that our proposal is really the most robust over other alternatives, classical parametrization like Mel frequency coefficients. So this is the work. I try to describe more details in what follows. The idea again is to have in the first stage of this representation an auditory model, an early auditory model. We really use here the SHAMA model. So then at the level of the auditory spectrograms, then we will try to apply these sparse techniques in order to get a two-dimensional representation of that mimics the cortical characteristics. This is a general scheme of this type of representation, this auditory motivated representation or inspired representation. So here you have the signal, acoustic signal S. Here is the Shama model. This is as output. Here you have this dimension, bidimensionally early auditory representation that we call here X. And then you have some bidimensional atoms associated to the spectrotemporal receptive fields. So the idea is here, you first have to estimate these atoms. That's the first part of the problem, estimate these atoms. And then you can use the atoms in order to get a sparse representation using these atoms. And you get a representation that mimics some of the characteristics of the representation at the auditory cortex level. So in this graphic, you can see how only very few of the coefficients of the representation are active for a particular time. Only very few of them. Each one of these are associated with this, each one of these spectrotemporal receptive fields. So the idea is that we use a Nausicaa algorithm in order to, with an iterative process, we estimate the dictionary and the coefficients. Now we don't go into all the details because of the time, but with this procedure, this is iterative procedure, that is, you try to maximize the a posteriori distribution of the probability distribution of the coefficients using the probability distributions. And some characteristic, for example, you can tell that the distribution of the coefficient is Laplacian and independent. The complete distribution, the conjunct distribution for the coefficient there. So if you propose that you can the whole distribution of all the elements of the representation is independent, so you can factorize the multidimensional probability density function into the individual ones, and you can make some type of optimal selection using this app. I don't know, I don't remember how is the name, but you try to go up in the derivative of this type of function in order to get the point of maximum probability for this approach. So,
Hello.
Yes, sorry.
Yes, sir. I had one doubt on the previous slide. When we are finding the sparse representation, is the X signal X auditory spectrogram or the original audio signal?
Yes, that's right. It's not S. This is not the temporal signal. Okay. This is the bidimensional signal. Mm-hmm.
The X. Auditory spectrogram. Okay.
Yes,
X.
that's right.
Okay.
That's right. Okay, and
thank
here,
you, sir.
Phi here is a dictionary, and the other here, this is a learning coefficient and all other details there that they are associated to the particular distributions you fix for each one of the components here. So if you apply this to some sounds at for example, at the C-level temporal scale level, you get some representations here. This is like the spectrotemporal receptive fields. And you can compare here one of them with a real biosignal, biological spectrotemporal receptive fields. And if you look at with some broad eyes, this is similar in some characteristic because only a few amount of the a portion of the energy of this spectrogram is interesting for this characteristic detector. And if you go at the phone level, you narrow your scale, then you have even more similar characteristics in your dictionary that the ones you find in the real biological experiments. These are also two examples from ferrets from the JAMA experiments. And all this dictionary is trained using many hours of the TIMIT database, the database that Prasanna mentioned in his last talk. So using many hours there of trying to look which are the most important characteristics in order to represent that phonemes with very few of these atoms. That's the idea. So this is a qualitative analysis only because we didn't compute any type of similarity index here, but you can say that you can see them very similar. So this is an important issue also, because in all of this, you only have to put some particular conditions in order to get the representations that are based on sparsity and independent of each one of the characteristics. And you get something very similar to the biological analogy. So then we apply this to some phonemes from TIMIT database, and we get the representations and try to see how this classification was degraded when you add some different quantities of noise, so different signal to noise ratio. So in this graphic, you have here in this axis the recognition rate. Here is perfect recognition and lower recognition in the bottom. So in the other axis, you have the signal to noise ratio. Here is the clean signal, and you have different signal to noise ratio here and until 0 signal to noise ratio. Remember that 0 signal to noise ratio is a very difficult environmental condition because you have the same energy in the signal than the energy in the noise. So most of the artificial systems fail to have good performance in that amount of noise. So here you have the different performance of the different techniques. For example, here you have classical Mel frequency Kestrel coefficients in green. Is this curve here? And as you can see, when noise, the amount of noise get worse, the performance drop very fast here. And when you use this type of representation that we are proposing here, you have really a gap between the performance of both systems. Even for more robust representations, like RASA PLP or probabilistic optimum filtering, or PLP only, you have worst results. So in this paper, we can demonstrate that this type of cognitive approach, really you can use it with benefits to the signal processing and classification algorithms. Well, but in another work, we then try to use this idea also for speech denoising, because one of the important characteristics of the SHAMA model, for example, is that you can invert the model. So if you have the auditory representation, you can also go backward and estimate the sound of the signal that produced this auditory spectrogram. This is an approximate solution, but it's sufficiently good, I think. So the idea here is also to change, because in the previous work, we used a representation of the spectrotemporal receptive fields that can be positive or negative in the values. But thinking about it, you have spectrograms there. So the idea is that they are always positive. So in this work, we use only positive coefficients. So we change the problem in order to get only positive coefficients and values in all the spectrotemporal representation. So we use really a non-negative matrix factorization framework in order to estimate the representation at auditory cortical level. And we propose a novel audio denoising algorithm based on this idea, with two dictionaries of atoms, one dictionary from the clean signals and the other dictionary for the noisy signals. I have to mention here that I forget to mention that in order to obtain the representation, we use here the MP method for matching pursuit method in order to get the coefficients. And here it's like doing some basic type of denoising for the representation, because if you select only the most prominent coefficient, you discard all the information regarding to other type of information not related to the phoneme, for example. But this is a very basic type of denoising that we use here in order to get a robust classification or a robust representation, trying to use the intrinsic characteristic of these representations. But in this other work, we use two dictionaries, one for clean signals and the other for noisy signals. So this is the details. These are the details of how we solve the problem we solve here with non-negative matrix factorization. We solve this problem. That is really we use a particular version of KSBD that Aaron and Elliot proposed for this type of non-negative representations. Forcing positivity is using this type of problem. So you can see the details in the paper. And here we have a diagram of how this method works. So again, you have the early auditory representation, but then you have a composed dictionary that some of the atoms represent the signal and some other atoms represent the noise. So you know which of the coefficients are associated to signal atoms and which of the coefficients are associated to noise. So it's very easy because you can do zero, all these coefficients. Then you selected only signal activations. And then from this activation, you can synthesize again the signal, the auditory representation, the auditory spectrogram, And you can use the inverse Gaussian model from SHAMA in order to estimate the signal that is the noise version of the signal. So now I will show you the results of this work. We also use, again, the speech, the TIMIT database. We use only 10 speech sentences of one of the speaker of TIMIT database. And also we use a NoiseX 92 database that is very used for this type of experiments, because you can add different type of noises to the signal using an additive model for noise. And then we compute 112 bidimensional atoms. Well, and all other details are here. So in the combined dictionary, we select 256 atoms with the most active values. And in order to measure the performance, we use different audio quality measures, objective quality measures like PSQ, PASQ, and the signal to noise ratio also. So here are examples of the dictionary estimate from clean signals. These are also, again, is frequency and time for each one of the atoms. And here is one example of the noising from a particular signal. Here is the speech signal from TIMIT. This is the clean one. Then you add some white noise at 0 dB, and you get something like this. As you can see, it's a very difficult condition, because you lose almost all the information in some parts of the spectrogram. This is the classical spectrogram. And then you can see, after applying the denoising method, that most of the important characteristic remains here. Well, this is all the different performance score that we compute for this work. I don't go much inside the details, but we compare this proposed with other traditional method that, for example, Wiener filtering or some spectral subtraction denoising method, or even some other non-negative matrix factorization algorithms. And the one we propose, that is here, and really it looks that our method in some of the situations, especially in very low signal to noise ratio, it behaves better than the traditional alternatives in most of the different quality measures. So this is all about the application of sparse representation to cognitive speech processing. So at this point, I want to know if you have any doubts here.
Hello?
Yes.
Yeah, sir. We have seen that we have used a dictionary for noise in this AACR. Suppose there is a noise which was not incorporated in our dictionary. How does this method perform for those noises? Can it perform better for unseen noises as compared to traditional spectral subtraction and other approaches?
Yes, that's right. If you this type of method, you need to know some characteristic of the noise. If you don't have it, it don't perform well, I think. So that's a limitation of this approach, obviously. Yes, you're right.
Okay. Okay, sir. Thank you.
Thank you, thank you. The idea here is to try to demonstrate the usefulness of all these ideas in trying to resemble some of the characteristics of the biological representation. That's the idea. But I think that there is a lot of work to do here. For example, I didn't see any work trying to use these representations in order to compress speech signals, like was proposed by the work Prasanna shows us of cognitive speech coding. There is no much works that use this approach. I think that you can really beat some of the classical methods of compressing signals.
Okay.
So
Okay, sir.
that's I think a good point to look for. Mhm.
Yes, sir.
So I lose the idea of the time. How we are with time? Because here in Argentina is 8:20.
Yeah, we have around 45 minutes, 40 minutes around.
Okay, okay, thank you very much. Because yesterday I go so slowly, so you can better understand what I am saying. So I have much stuff in order to discuss today with you. Please, Yaga, can you stop me when you get the time? And
Yes, yes.
perhaps some of the material I can also use tomorrow in the class, in the lecture of tomorrow.
Yes.
Thank you. Well, I will go on. So
Sir,
another, yes,
so
yes.
we have one more doubt. Sir, like cognitive speech processing, we move towards it because it should be inherently robust to noise, like we are, like human speech, like human recognition is. So, but in our model, is that robustness coming only because of seeing the dictionary or developing the dictionary, or is there some way, another way to introduce that robustness? Like we are not necessarily, we need not see all types of noises before we try to suppress when we are, as humans, when we do speech recognition in presence of noise. We need not see all types of noises, but here, how do we bring that component in using CSP?
Yes, the robustness is intrinsic to this type of representation. I go to one of the previous slides, I think here. Here. Here you have an example of a sparse representation. So as you see here, only very few of the elements have high values. So if you use some type of threshold here, you can surely eliminate all the information different from the one the dictionary is trained for. So if you train the dictionary only on clean speech, if you don't use any information about noise, only with this very simple approach, then only with the threshold, the information of the noise components, you hope that is distributed over all the components, over all the atoms, because you need the sparsity constraint is only applied to clean signals, to clean speech signals. So when you have some signal that you didn't use for train, then you haven't this sparsity property for that type of signal because you don't use in training. So many of the coefficients will be activated there for another type of signals. So if you put the threshold, as I mentioned, you can easily eliminate all the information for that type of signal. That is the intrinsic robustness of this type of approach. Or instead of a threshold, you can also here use matching pursuit, and surely you can select this coefficient and this coefficient. For example, if you try to apply the algorithms in 3 steps, then you get surely these most prominent the values of the representation. So all the others are eliminated with this very simple procedure. Of course, noise also affects these coefficients, surely. But most of the time, this type of the noising method retains the more important information from the signal.
Okay, thank you, sir. Thank you so much.
Thank you. Thank you. Well, I will briefly describe other intelligent speech processing methods that in our group, and especially in collaboration with Professor Prasanna, we implement and propose some years ago. Is this work from 2016? In this work, we try to optimize also the filter banks. In traditional NFCC analysis, you have a filter bank, and the idea here is that that general filter bank that is really estimated by means of psychoacoustical experiments, the Mel frequency spectral distribution. But the idea here is for different tasks, really you have different type and possibly different filter banks that are optimum for this particular task. So in this work, we try to optimize the filter bank. I think that this optimization is an intelligent approach because using information about the signals that you want to, for example, classify, you can optimize also the frequency distribution of the filter. That's the idea here. And we try to classify different type of emotional speech, particular stress speech with different databases. So here's a diagram of the proposed methods. You have here the speech sentences. Like in Mel frequency Kestrel coefficient, we produce a windowing of the signal, then you compute the spectrum and you have the filter bank. But this filter bank will be optimized by the means of a genetic algorithm. Yeah, the rest of the stage of the in order to compute the coefficients are the same from Mel frequency coefficients, Kestrel coefficients. So then we apply some classification technique like support vector machines, and we can estimate the motion of this speech sentence. So in this work, we use two emotion speech databases. One of them is really very difficult task because you have some spontaneous emotions from child, I think. They show, I think, by videos. No, the child interact with the robots, with robot, and the robot talk to them. And so they elicited some different emotions in the child. Angry, touchy, emphatic, positive ones, joyful, all of this. And then you have all this database in order to try to classify the particular emotion. This is a very, very difficult benchmark for emotion recognition, at least in this. At the time we published the paper, our results are the best results obtained with this database. And the other database is a database in Hindi that was recorded by Prasanna group in India. Here are 15 speakers, and they try to mimic the different stress conditions. This is an active database. It's a little more easy, the classification task, because it's not spontaneous emotions. Mhm. So here is the result of the optimization with the genetic algorithm. I think that the trick here is to get a low dimensional representation of the filter bank using splines. We use splines here in order to get a few parameters to adjust or to optimize in the solution space for the genetic algorithm. So it is with touching these few parameters, you can get different type of distribution of the frequency of the filter bank and also the amplitude of each filter. So this is the result. This is a classic MCC, NFCC filter bank. This is from one of the database. This is from another, and different examples here that you can see very, very pronounced difference between the classical approach. But these filter banks are optimized for the particular task. So, of course, the results are better. As you can see here, from this type of new representation here, the one we propose, for each one of the databases. Here is the Hindi corpus, and here the FAO Evo corpus. And we get, for most of the emotion, we get the best results, as you see here. As you can see here, this is very, very difficult database. These are the best results until the publication of our work. Well, with this, I finish this lecture, but in what follows, I have to present you some another lecture. So if you have any question of this last method, I hear them, or in another case, I will proceed with the other lecture. Or just begin the other lecture. I think that I get 30 minutes.
Yes, it is around 30 minutes.
Okay. I think that I can begin. So here are all the bibliography, the papers, if you want to then to look for them and look at the details of some of the methods. Well, okay. I will change now the presentation. Well, the idea here is to present all the speech-related video signals, not only the acoustic one, but all the other related video signals, even the brain-related video signals. So as we mentioned in the first lecture, I think, speech communication is really the most natural way of communication, and it's the most studied signal also, and it conveys really a lot of information there. So in classical analysis of the voice signal, we use acoustic signal, but we have also many other signals in order to extract information from the process. Not only production, but also perception of the speech signal. So as we just see, human oral communication is a very complex physiological process that involves interaction and coordination of various parts of the body and produce many signals. All the signals can be measured and analyzed. Here you have a general diagram of all the process beginning with the idea in the speaker or the message in the speaker, and from this type of acoustic signal, the listener can understand what the person is saying. So this is the complex process in one direction, from the speaker to the listener, and inside the brain of the listener, all the process in order to understand what the speaker is saying. We will review some of the details behind this process, the production, and also the perception in what follows, and next lectures also. So first issue here is to try to classify the different spoken modes. Because in traditional and normal recording of the acoustic signal in normal conditions, you use the acoustic signal, but the speakers have also different modes to produce the speech signal. So the classical ones are with acoustic output. So here you have the ones with glottal activity. So you use here the vocal cords here. You use the glottal activity in order to produce a speech. You have two types of speech, the modal or normal speech, and the whisper speech. We will see the details later. And then, it depends on the level of effort, you also have a normal speech, shouted speech, or murmured speech. This classification is taken from this work, the DC review of this biosignal related, speech related processing. But we also have some speaking modes without acoustic output. In this classification, you have silent speech, imagined speech, and inner speech that we talk some, we give some ideas, we get some idea in the previous talks. So we will have some details here. So with respect to the classification, depending on glottal activity, a modal speech is the one where vocal folds vibrate for voice sounds or do not vibrate for unvoiced sounds. And in whisper pitch, turbulent flows through a constant aperture formed between vocal folds, resulting only unvoiced sound. No voiced sounds were produced using this modality of speak. So here in this graph, you can see in the upper side of the graph, you can see normal speech, modal speech in this classification. And here is the whisper speech. that is really more difficult to understand. And several methods are proposed in order to recognize this type of speech. So according to the level of effort, we have normal modal speech. That is modal speech at normal intensity. This is the standard mode of speaking, the traditional mode of speaking. And then you have shouted speech. For example, if you are angry, then you can shout. And in this case, this type of speech is characterized by higher intensity, higher pitch, and a more open articulation. This type of speech shares common properties with lumbar speech produced in noisy environments. When you have a very high background noise, for example, inside the cabin of an airplane, then you modify your phonation in order to try to better enhance the acoustic cues. This type of modification is similar to the one produced during shouted speech. And then you have murmur speech. This type of speech is characterized by very low intensity, but you have voice and non-voice sounds here. But they are difficult to perceive and only perceived by the person that are near the speaker. Some residual acoustic activity can be recorded, but using only a specific microphone. So all these speaking modes are with acoustic recordings. They are with acoustic output. But then you have some speaking modes that are perhaps the most interesting for us. That there's no acoustic output. The speaker don't produce any sound. So we have here silent speech. The speakers in silent speech are instructed to move the articulator, the mouth, the tongue, all the stuff, the lips, as is producing normal modal speech, but to suppress their pulmonary air seam so that no sound is emitted. So only you move the different parts of the vocal tract, but you don't produce any sound. Imagined speech is another modality similar to silent speech, except that movement of the articulations are also suppressed. So here you try to imagine that you pronounce the sound, but it's especial attention, the speaker have to put in the articulation of the sounds, but without doing any movements of the articulators. And then you have inner speech. In inner speech, really there are a broad range of description of inner speech in the literature. Most of the authors speak independently, use independently both terms, imagined speech or inner speech. But I think that they are different type of speaking modes that is proposed by Schultz in this work. We use the similar definition of inner speech that the one proposed in this work. We define inner speech as an inner process, internalized process, in which one thinks in pure meaning, but we add here that in general, this process is associated to an auditory imagination of your own internal voice. Not only pure meanings, but in generally, you also hear inside your head this inner speech. This we will go through more detail in what follows, but this inner speech phenomenon was very broadly studied by psychology and some neuroscientific researchers in the past. So we know really we have many descriptions of this phenomena, but it's until very in the last years only that we have useful signals in order to measure this type of phenomena. So I think that that's the reason, because of the confusion between terms, because it's really a very new field, and researchers are really trying to define all this stuff, starting by the measure of the different signals. And also, the important thing here is which the subject is told to do. Mhm. The consent of you get the command you get to the speaker is, I think, is the key for what type of phenomena you are really measuring. Also, we have to take into account many different aspects in the experimental stage, because it's very difficult to isolate it only the part of the signal associated with this type of phenomena. But we will talk about the details in the next lectures, I think. So, really, apart by sound, there are many different physiological measurements that and sensors that we can use in order to get information about, for example, the speech production process. This is an image taken also from the work of Schultz. And here we have the different activities associated with the speech production process. So you have, of course, the brain activity, you have muscle activity, you have articulatory activity, you have also laryngeal activity, and also respiratory activity. All are important in order to recognize, for example, speech. And if you have some hard environmental conditions, perhaps you can use complementary signals from complementary sensors in order to get a better performance in order to recognize speech. That's one of the motivation of using this type of approach. Well, now we try to see different type of signals and try to describe the principal characteristics of each one of them related with the speech. So one of the main, apart from brain signal, one of the main important signals are the ones derived from muscle activity, the EMG, electromyograph signals. Also, the one associated with changes in conduction at the level of the larynx. This is what's called the electroglottogram, and it's very used in speech related research. Then you have electropalatography, that you can measure some of the important position of the articulator, like the tongue and the lips and all of this. And also electromagnetic articulography, less used than the previous ones, but there are some works using this technique also. And of course, different type of images and videos derived with different techniques like ultrasound. that gives some insights about all the production, mechanical, for example, properties of the articulation process in order to get the signal. And of course, all the related to brain activity, like EEG that we discussed in previous lectures, ECOG, FNIRS, etc. And these, of course, are very interesting because they are related with brain-computer interface, as we saw yesterday. So let's start with electromyography. Well, electromyography is a technique in which you can register the electrical activity produced by muscles at the level of the skin. So you put some electrode in the skin in different parts, and you can record it, the electrical activity associated to the muscles movements. The surface electrodes offers a non-invasive way or way of register, because you also have needle electrodes that go inside the skin, like in acupuncture. And the idea is to use this type of non-invasive resistor in order to evaluate the articulation and different movement of the speech muscles around the region of the face and the neck. So the electrical source is a muscle membrane potential of about minus 90 millivolts. EMG potential range between 50 microvolts and up to 30 millivolts, depending on the muscle and the position of the electrodes. The typical repetition rate of the muscle is about between 7 and 20 hertz. And as already said, this can be used as alternative for complementary information in very noisy environment for speech recognition. Here you have a typical setup with this particular equipment, the wireless equipment, in order to register the EMG at different points, here in the face and in the neck. And here you have the different signals recording in each of the channel, while the speaker is pronouncing this sentence, "I am not ready yet." Here is the temporal evolution. So we can do some type of automatic speech recognition using only this signal, or combining these signals with the acoustic one. That's the idea. Sorry. I am a little tired. My voice is tired. So another signal is electroglottography. This is a very, very used technique to register the laryngeal behavior indirectly by measuring the change in electrical impedance across the throat during speaking. The idea is that the high frequency electrical current of a small voltage and amperage pass between two electrodes situated here. And then with this high frequency, you can measure the changes in conduction of the in the neck. This method was developed 60 or 70 years ago. And nowadays, there are several commercially available devices or equipment in order to measure this type of signals. So this is an schematic view of one of these devices. So this is, you can look here, the position of the electrodes. And when the vocal cords periodically open and close, as we can see in this frames or for a video, putting a camera in this direction. The camera with an endoscopy camera, you can go there and look from this point inside the trachea. So you can see that the vocal cords are initially closed and then in successive frames open and then close again. So when both cords get in touch, impedance change, and we really we know the process. So you can get some signal with this type of waveform here. And each one of these correspond to the period of opening and closing of the vocal cords. And well, there's a lot of studies of research around this signal in the here in this bottom graph. You have the derivative signal of the EGG. And with this signal and other more complex signal processing techniques, you can estimate the moment where the vocal cords closed or open. And this is important for many techniques of speech signal processing.
So we can stop now. I will start the tutorial maybe in 2-3 minutes. Let's have time.
Okay, thank you, Yaga. I think that the rest of the slides I can use in the lecture of tomorrow. Thank you very much.
Yes. Hello. Good afternoon to all. So, am I audible?
Yes.
So my screen is visible, correct?
Yes, it is.
Okay. So now we will. This is actually the third day tutorial session. So we will discuss about EEG signal processing and basic brain-computer interface. So here I will just okay. So we will just see how the EEG signal processing we are doing, and it's like pre-processing steps to going before going for any BCI application or brain computer interface applications. What are the pre-processing steps we generally have to follow? So that we will demonstrate in this session. So for that, what I have done, there have recently published article by Professor Ruffiner and their team. So they have collected a data for that EEG data with inner speech, visualized speech, and pronounced speech. So if I will just tell some parts. So in the overview of the data set. So this data set have around 10 subjects. So from the out of 10 subjects, so each subjects has gone through 3 kind of recording sessions. Okay, of course, each session have the inter-session break, and before the recording there is a baseline, so which will record the EEG signals without any kind of any kind of excitations or any kind of visual representation or visual stimuli, any kind of stimuli. Before any kind of stimuli, so they will record baseline for 15 seconds. Then they will go for pronounced speech, some n number of trials, inner speech, then visualized speech and visualized condition. Okay, so in this way they have recorded the data. So these are okay, so next, this is the way they have recorded. Initially, with this from starting from time equal to after this 15 seconds baseline, this time is equal to 0 second. Then after that, they will give up, down, left, right options. This will come randomly for each trial. So then the clue will start over here in 1 second when this blink will come. Then the after that only this subject will start thinking about the word of up, down, right and left. And after end of 3.5 second, again there is a 1 second of relax interval. Then after that the next trial will start. So this is the way they have recorded the data. So for the data acquisition, so they have collected in 128 EEG channel, and we also have 8 external active EMG channels. So each data are recorded in 24-bit and 1024 as a sampling, 1024 as a sampling frequency. Okay, so next, okay, so another thing I will just want to tell. So in the data pre-processing processing part, we will see these kind of events: raw data loading, event checking and correction, and then a re-reference using that baseline. So for the baseline, they're out of 8 EMG channels. So they have used EXG1 and EXG2 for baseline. Then we'll go for digital filtering, epoching and decimation, then independent component analysis, ICA, to remove the artifact. Then the this is known as EMG control. So electromyography control. So this actually there have another 2 channel called like EXG1, 2. There have EXG7 and 8. So using that 7 and 8, so they want to tell that if there have in general in inner speech there should not have any kind of mouth movements. So this actually EXG7 and XG8 will capture the mouth movements. So if the variance of there have actually a threshold with the mean and variance of that power of this 2 signal, EXG7 and EXG8 channel, the signal captured through EXG7 and EXG8. So if that is crossing the threshold of this one, so then they will tell that this may not be useful for inner speech representation or kind of thing. Okay, so the database structure is like this. Maybe the next one is the events. So there have around some events associated with the timestamps. So actually in one easy file, all the events you will get. So we'll see that part now. And if we go for the statistics, so there have 10 subjects, and each subjects have spoken pronounced speech, inner speech, and visualized speech. So this is the statistics how they have spoken that. And after before going to any kind of classification task like BCI applications, so from the initial events, they have converted it to, we have to convert it to this event statistics. Okay, whatever written in the event, table 5. So first column of the statistics should contain the sample number. Second one will be the trial class, either up, down, right, left. And the third one will be the condition. Is it pronounced speech or inner speech or visualized speech? The fourth one is the trial sessions. So we'll see how we are creating this in the coding part. Okay, so and there also have a report file which contains this information. So we have to create a report file which will now we will create a report file which will contain the age information, gender information, the recording duration. They actually conducted a answer right or wrong, means to see the attentiveness of the subject. So they randomly given some questions and asked the subject to respond it, and according to the right and wrong of that answer, so they can see that is that subject is attentive to perform the task or not. Okay, so that information also they are capturing over here. So next one is EMG trials. This will be and the power EXG, that what is the power of EXG 7 and 8. Then obviously the mean of this one and standard deviation of this one. So this they will capture in the report file. So that is okay. That is all about this part. So let's go to the coding part and see. So for that here first case I have just imported OS library and
Excuse
NumPy.
me. Excuse me. In this case, which electrodes were used to collect the data?
So they actually have taken EEG recordings, some 128 channels, and some 8 electrodes EMG or ECOG.
Yeah,
channels.
but in that it is specific type of.
So they have used BioSemi some tools. If Professor Rufinar is there, he can clarify. Okay. Or else maybe.
Yes, which is a question?
Sir, the question is some what kind of electrodes people have used to record the data.
Yes, as you said, there are 128 electrodes and the EMG electrodes in order to control the movement of the masks. And the disposition over the head is the traditional one, the 1020 international systems in order to put the electrodes in the head over the scalp.
Okay,
I
sir.
don't know. Is that the question?
Yeah, thank you. Now I wanted to know that whatever electrode, because there are different types of electrodes. So exactly which type of electrode was used?
Okay, I don't remember here. I think that the details are in the paper.
I am showing that.
Yes,
It is showing
I will
that-
go through. I will
Yeah.
go through it, sir. Yeah,
Yeah.
thank you.
Electrodes were filled with Sagna gel. They are gel electrodes.
Okay, sir. Thank you.
The complete process to put the electrodes on the gel is very something like half an hour in order to prepare each one of the experiments.
Okay, sir.
Thank you.
Okay, thank you. So now we will go. Any other doubt? Anyone have?
I remain here as you need more clarifications.
Yes, yes. Sir. So we can here I am importing the OS library and NumPy as NumPy. Okay, so maybe this folder we have shared in today morning. So I hope that you people have downloaded it. So if you have downloaded it, maybe you can load it to your Jupyter notebook. If you are facing any problem, let me know. I can also help you out. So once you load it, then you may not have installed the MNE toolkit. If you have installed, then it's fine. Or else maybe this command you can use to install this. Just uncomment this one, the hatch command, and run this. Then you can able to install it. Okay. if you will do parallelly, I think it will be better. For any problem, if there's any problem, you can clarify it here. Okay. So the next part is once the MNE library is installed, if you want to check is it properly installed or not, maybe this command you can run. And the detail of the library, you can the link I have given here, you can go through and see what are the details of that library and how to install and what are the systems available. And they have very good tutorial for each and every functions available in the library. You can go through it. So next one is to run this script, we need some kind of environment, a specific version of Python, as we have discussed in the Python tutorial. So maximum of the codes are whatever we are writing, this is sensitive to Python version and even all other packages version. So here, if you have Conda, you can you don't have to be worried. If you don't have Conda, you can see the procedure how to install Conda over here. The links are given. You can install on your own on your system. Once that is done, you have to go to this is actually by one of the PhD scholar of Professor Rufiner. This I have just forked it from his GitHub library. So this is actually they have written for how to do pre-processing with this data set. Okay, so for that you have to create your environment using Conda. Okay, that environment.yml file is available over here. If you open this, it needs some kind of Python version of 3.8.6 and MNE version of 0.22.0 and Spider of 4.2.1. So these are the versions it is required to run this script. Okay, so for that you can in your terminal you can run this command. I can show you. So this command you can run such that this path will be created. Once it is done, then you can just have to write Conda activate inner speech. Okay. So till this point, anyone have doubt? Okay.
No doubt.
Okay. So now what I have done, so I can show you once the data set. This is so this is actually the dataset structure. So this is the subjects. We have seen this 10 subjects and each subjects have some 3 sessions. Okay. So I only have taken for this pre-processing demonstration, this is the first, this PDF file I have taken, subject 01, session 1. This file I have taken over here. Okay. So I just have given the path over here, and now I am reading this data using MNE IO library. All the files has been encoded in .bdf format. Okay. So the reference paper is over here. Maybe whatever I have shown you, can go through it. Yeah. So once that is done, by using raw data.info, you can able to see what are the things available in this data. Okay. So if you run it, you will get this. So as we have already discussed, this have 136 channels, 128 for EEG, and another 8 is for EMG signals. Okay, for muscle activities. So and the sampling frequency is again 1024. Okay. And the high pass filter is of 0 Hz. The high pass filter has been placed, and the low pass filter has been placed on to 208 hertz. So each signal has maximum component of the signal is around 208 hertz. Okay. So now we have seen from the paper that EXG1 and EXG2 are the baseline signals. So I have set it as a reference signal, and I assigned it to as set EEG reference. So for the baseline activity. Okay. So I have run it. So for this. So now next one, if we want to see how there have around 136 channels. So how will be the power spectrum of your recorded signals? So you can see this using this raw data.plot power spectral density command. So here I have taken maximum frequency up to 100 hertz. Okay. So though it have the signal component is still 208 hertz. So I am just considering till 100 hertz. Okay. So now you can run it and see this. Yeah, as in the first lecture, Professor Rufiner has already has been commented on this. So that due to some power supply there in 50 hertz power supply, that due to that there have some kind of components, high amplitude components and 50 hertz. So the ideal the thing will be we have to first notch it, this frequency component. Is it due to this power supply as this is happening? So we have to notch it. So you have to first use a notch filter which will remove that 50 hertz component. Okay. So for that I have same with MNE library.
Yeah,
If you
excuse me.
write, yeah, please.
By observing this graph, one observation is that whatever 128 channels the signal is picked up, they are
Yes.
plotted superimposed on one another.
Correct.
And if we see the trend, initial low frequency comparatively amplitude is more, and then it is decreasing. So even though this particular activity may be for the silent speech, or that person is observing that arrow up, down, and actually speaking. So this is for first category. Why all the channels are picking up the signal more or less which looks similar? According to me, only few electrodes they should be picking up, because brain activity will be more relevant to that particular region. But here I am observing that all the electrodes they are picking up the signal whose characteristics is similar.
So Professor Ripner, have any comments on this? Hello.
Yes, this is precisely inner speech condition, resistor for inner speech condition. Surely there are some electrodes with more activity than others, but in this, I think, early work, we only present all the data. Then you have to try different, for example, procedures in order to select the most important electrode or something like that. But in this work, we use all the electrodes, and we present all the data for the different modalities.
Okay, okay, sir. Thank you.
Thank you. Thank you. So now okay, so in this case I have used a notch filter to remove the 50 hertz component over here. So after that, if we run this block and see the power spectral density again, so you can see there is a this component has been removed for the 50 hertz case. Okay, so now after that we have to we have to do a band pass filtering with a log cutoff of 0.5 to 100 hertz. Okay, so for that I am using raw data.filter function of same MNE toolkit. So it will, if we give the low frequency cutoff and high frequency cutoff, it will do the band pass filtering. Yeah. So after doing the filtering, you can again plot the power spectral density to see. If you see this, there is a dotted mark over here, so it has been removed till 0 to 0.5, and after that till 100 hertz, this is the intact. The values are. So now next part is how to see the time domain signal of this whatever the E's we have recorded. So for that you can directly use raw data dot plot, and this duration and n channels. This is to see the screen till 4.5 and 5 channels. You can go on increasing and reducing this to see the other parts. So let me run this. As I'm using now this Jupyter notebook, I don't have a flexibility to choose this one to up and down. If you are using some Spider notebook or something, you can directly run this and the screen will pop up. You can choose for different durations and different, this blocks will come down and up and down, and can see different channel, what how the signals has been recorded, and with the different time duration you can see this. Okay. Now about detecting the events. So to detect the events, so we have already seen we have many events from the paper. Uh, this one. So, open that. Yeah, there have different events corresponds to start protocol, end protocol, start baseline, end baseline, and from starting up, down, right, left, and all this. So these are all events. So at a total, there have around 1113 events found over here. Okay. So now. Okay, so now in the check baseline events, they actually created one function which will check if the events tags are correct or not. So once they got the recording, they have find out that some parts are have some mistakes. So they have designed these functions to correct this out. So if you run it and so it will check the baseline tags. Next one, if there have any error, so it will correct it. So it is telling tags are correct. All these are correct. Only one warning there have missing rest interval I equal to 23. Okay. So now, as we have seen that paper have a report column, so which have age information, gender information, and recording time information, and all this. So I just have created a dictionary, age, gender, recording time, and that questions they randomly ask to see the attentions of the subject. Is he or she is attentive to the task or not? So this will tell if they are correct or wrong for all the trials of that speaker for this respective session. We'll store that. Okay. So now, if I will run this. Okay, so I have taken this cognitive control. You can see this. There have out of 45, only there have 2 events which are answered as wrong. So maybe in the 2 cases, the subject are not attentive. Okay. From the start. So till this point we have covered this part. Now it is generating the report. Okay. So now picking the EOG signal. So what actually it is doing, is we generally focus to do for this task some classification task with respect to, suppose, up, down, and left and right. These are the four stimulus we have given to the subjects. So we have to pick out our data for that with different conditions and different classes. So conditions means in this case we can tell this either it is a pronounced speech or visualized speech, or it is a inner speech, or in the next case that maybe the classes are up, down, and left and right. Okay, so with respect to that, what here we are doing, that EOG, that 8 channel signals we are trying to find from the whole raw data. Okay, so there, that's why we what actually we have written here. So the event ID is this one, and we are downsampling with a rate of 4. As our sampling frequency here is 1024. After downsampling, it will go down to 256 hertz. Okay, now picks EOG, I am writing the raw data and info, and EEG I am giving as a false. Only include the channels EXG1, EXG2, EXG4, 3, 4, 5, 6, 7, 8. Okay, all this muscle control that EMG signals we are taking here. Okay, so this epochs, when I give the event IDs, it will give me the output of that one. Okay, so let me run this. So you can see with respect to this 8 electrodes what we have placed for muscle control. So this kind of signals it is capturing with different epoch numbers. Okay. Now if we see the epoch info here, there have around 8 channels, as we have kept only taken 8 channels, and our high pass frequency is 0.5 and low pass is 100. Okay, and we have taken 8 channels and the sampling frequency has been reduced to 256. So this is decimated over here. Now on the next block we are defining our baseline. Okay, so the baseline T event ID is 13. Okay, so now I am generating the T baseline time index for the baseline. Okay, so using that I will compute, I will epoch that from the raw data, and I will get the baseline as the output. Okay, so then after that I will plot the baseline signal using baseline dot. Okay, so this is how it will come. As we baseline have all the channels. Okay, you see the baseline dot info, it will tell that all 136 EEG channels are there. Till this point, any doubt?
No, what is the difference between the previously plotted graph where you had shown overlapping of those EEG signals and what you are showing now here? Should
Okay,
they,
so
should
this
they
one,
be same?
this one,
Not this one. At the beginning, you had shown the overlapping of all the 128 channel EEG signals. Yeah, this
okay,
one.
these are the power spectral densities
Power
of all the
spectrum.
channels.
Yeah, but below
Yeah.
that, I think time domain
Below that, I have shown you the time domain signal only for 5 channels.
Acha, so now it is for all the channels.
It is for all the channels.
Okay.
I have this one is I have extracted for only that EOG signals.
This is for EOG. That is
8
correct.
control signals what we have taken. Okay. Then this one I am telling about the baseline, the two signals they have recorded before the stimulus starts.
Okay.
So this was, you can see more clear kind of thing before stimulus starts.
All right. Thank you.
Okay, the next part is now we have to find with respect to our other epochs, other events that we will put our event ID and will capture the all EEG signals, and we will exclude the all the control signals over here. Okay, so I have plotted for again for channel for 5 channels. Okay, so you can see this these are the EEG signals for this time interval kind of thing. It's not, the baseline is not there, so only for the events it is they have picked out the signals. Okay, EEG signals. So you find the info of that, we have a 128 EEG channels, and similarly high pass frequency and low pass frequency we have, and the sampling frequency is 256 hertz over here. Okay. Now for artifact removal, we have to do the independent component analysis. So for that, I have taken all the channels together. In this point, we have only taken 128 channels. We have removed the external activities. So in this case, we have taken all the channels, okay, to get the poked version. See the info, we can see this, all the 136 channels are there. Okay, so with 256 hertz is the sampling frequency. Now for independent component analysis, what actually it will do, so suppose there have a as we have some different control signals we have taken, you can, if you go through the paper, you can see that where this control electrodes have been placed. Okay, so for them, actually, if there is a eye blinking kind of thing or different other activities, so this will give a sudden change in the EEG signal. To remove that artifacts, generally people use independent component analysis. Actually for their task, they have used some parameter for ICA is this one, but it takes lots of time to compute that. For demonstration purpose, I just have taken a small one. Okay, maybe if you are near your system, lab system, you can run with this and check. It may take some half an hour time or 1 hour time, depending on your system ability to get the ICA components, if you put the ICA fit kind of thing. So here I have just given some 20 for demonstration purpose.
Yeah, but how it will be decided which part of the EEG signal will be processed for the ICA?
Okay, so actually what they will do, first they will compute the, first they will fit the ICA function over there. And then after seeing the variations on that ICA component, they will exclude the channels, that artifacts using that ICA matrix per dyno. Is it clear or?
Yeah, okay, right.
So now once, okay, so it will take some time. So once it is done, we will find the bed EOG signals. Okay, by projecting the epoch signals with respect to different control signals, 3, 4, because 1 and 2 we have used for baseline, and other channel signals we will use to remove the artifacts over here. Okay. So once that is done, then we will apply this ICA to epoch EEG signal to get the final output. Okay. So you can see in the earlier version, what we have seen over here, this is more kind of clunky kind of thing, and it is not clear even all the signals. You see somewhat we have got the clarity. Maybe if you run the whole part, whatever they are suggesting, maybe you can get some better clarity on the signals. Okay. Now, for the standardization of events, they actually defines different functions which will take actually their events, all the 1113 events, and actually after that it will give you a set of events whichever is required for our classification task. Okay. So if you see the initial event set is 1113 cross 3. After adding the condition tag and block tag, session tag, and removing one trigger from that, and we will standardize the labels. After that, we will get around 200 cross 4.
No, can you please explain again what is this?
Actually, they have multiple events, correct? For each cases. So they have in a total of 1113 events. Okay, and these three is first one is the starting point, and another two will be some triggering information, and another one one will be the one is their class information. Another one is the event when the signal is starting point of that event. Another second one is I think some trigger information. I forgot the column what belongs to. So that actually they are removing these trigger events. You see here that triggering events they are removing over here from here. So that maybe if I correctly remember, that maybe due to this this trigger event, the second one what they are removing, that is what they have given the one questions to see the is the subject is attentive or not. So that information they are collecting with that tag that will not be required for us for classification task. That's why they are removing that one. Okay, and another two tags they are adding. One is the condition tag, another one is the block tag. Condition tags are that I think with different this inner speech or visualized speech or this one. Another one is
Pronounced.
visualized and pronounced. Correct. Yeah, pronounced speech. For these three, the conditions they are adding over here. And then after that, whatever the with respect to the classes, whatever the events are required, they are just shortlisting that. So after that, we are getting around 200 cross 4 events. Okay.
Yeah.
I
okay,
hope it is clear.
Yeah, thank you.
Okay, so already that has been done. Again, if you do not no issue. So after getting that, so now what we have to do, we will do that EMG. We will see that how to do that EMG control sequence. So we have seen that we need some kind of thresholding. We will do some thresholding with that if that inner speech whatever they have collected is correct or not. For that, there should not have any mouth movement. So they have placed 2 electrode EXG 6, I think 7 and 8. So from that, they will compute the power and power, and they will compute the mean of the power and variance of that, and accordingly they will show that what are the channels or what are the trials has been crossing that one. Maybe for using that information later you can remove that from for the task, as for the final task you are doing, if that is not useful. Okay, so here what I am doing, I just have copied my baseline signal whatever initially it had, and I am filtering the baseline signal from using a low pass filter at 1 hertz, low pass frequency at 1 hertz and high pass frequency in 20 hertz. Okay, so after that, this is telling the what is the sampling frequency of this one, frequency count, and then I am just copying it to another variable. That's all. So after filtering, I will get up to 1 to 20 hertz component. Maybe the signal energy is more in 1 to 20 from the power spectral density. They are choosing this 1 to 20 hertz. Okay. So this is the way we have from the paper. We have seen there. Let me open that. They are computing the subtime window-based power. So with a 0.5 second as a window length and a 0.05 second as a shift, time shift. So this part actually done here. So it will take window length and window step information and the signal and sampling frequency, and the T minimum, the time minimum and time maximum from here, and it will give the final signal. As we have seen this, from 1 to 3.5 is important. So in this case, they have taken from the figure, if you see, 1 second to 3.5 is the actual time of when the subject can think on that and produce some kind of maybe some EEG signal. It will be captured on that time, will be more beneficial for the stimulus. So for that, here if we go, we'll see this window length we have taken 0.5 and 0.05. Okay, and I had taken the time T minimum as 1 to 3.5. Okay, over here, and the baseline, for baseline I have taken 0 to 15 as we have discussed. So I am taking EXG 7 initially. Okay, then using that, so okay, so using that, if you put get data, you will just get a data, all the data of that. Okay, so once you do that, then if you pass through the calculate powered window, so it will give you the mean energy and standard deviation energy, okay, of that channel, EXG 7 channel. Okay, so I have not done this problem. So similar things, we also have to do the same thing for EXG 8 channel. And after that, they are computing the threshold as given in the equation over here. So threshold equal to mean of this one and plus standard deviation of this one. Okay, so what they are doing here, EXG 7 and 8, they are copying and they are finding the okay, so now for other EEG signal EEG channels, so they are for okay, so for other trials actually they are computing all the okay, trial power and or 7 and 8. Okay, for the different event trials. Okay, so if that event trials is crossing greater than to your threshold or threshold 7 or threshold 8, so you can see this threshold 7 and threshold 8 are the this equation, mean plus standard deviation plus standard time series. Their gamma they have considered as 3 into your standard deviation. Similarly, 7 and 8 they have written over here. So if it is crossing this, then they are telling you reject that trial. Okay. Is it clear till this point?
Yeah, yes, sir.
Okay, so after that, so they are updating the other report values like EMG trials and your power EXG7, what is the power of this EXG7 channel, 8 channel, and all the baseline, mean, and standard deviations over here. So now, suppose these are the pre-processing steps we already have done. Now, if we want to go for a classification task, how we can extract the data from our EEG channels. Okay, so we have stored in epochs EEG. Now I am computing the data. If you put epochs EEG.data, you will get the data. I can show you the how this data size. If you put data.set, run this first. You can see this all the 200 events we have and 128 channel and this 1153. So if you see this 1153 belongs to your 256 into 4.5 around. So this is my whole data. So now again I will choose from so time window, as you have seen, I will take on 1.5 to 3.5 as the time window for any classification task. So sampling frequency I am taking is 256 Hz here. So we have downsampled it. So now the data will be select time window of this one. Okay. Again, I have to run this first. Okay, so now if we open another block and see the shape of data. I'm able to see now this earlier it was 11:53. We have just cut the time from 1.5 to 3.5 seconds. Now it will be on 512. Okay. Now I am filtering the condition. With respect to condition, this will be either it is be pronounced inner or visualized. Okay. So with respect to that, you can according to your condition tag, you can able to filter that out using this function. Now this is for with respect to class. So either up, down, and left, right. Okay. So you can condition it 0, 1, 2, 3. Okay. So it will take input either if you are giving up, you need up only up or down or left and right. Accordingly, it will give you the X data and Y data with respect to your first column value. Is it if it is equal to the class tag. Okay. So let me invoke these functions first. Now, suppose in this case, I want to classify between up, down, and left and right of all the conditions are inner speech. Okay, so then you just have to run this. Okay, and now this transform for classification. This actually inside this it will call this filter condition and filter class, and finally it will give you the final metrics. Okay, so if you see this one is my y is 200, this is event id 204. Okay, so now once I will run this block. This will be I am giving input as all data, and this is my event IDs and classes and conditions. If I will give it, so it will give me the corresponding data and corresponding labels, class labels for that. Okay, so after that I am getting x of size 80. So now there have only 80 events which belongs to this one. Having condition inner and class as up, down, left, right. Okay. Then if we see the y step, this is 80 labels we have. So now if you want to see the y values, you can just print it and see it. So you can see 0, 1, 2, 3, 4, 2, 3 are the 4 classes. So 4 labels are here. Okay. So have any doubt till this point?
No, don't work.
Okay. So now if you want to download the full data set, maybe for tomorrow or day after tomorrow, we will do the classification task. I think it will be better if you download all the files and come to the lab tutorial sessions, as that you can also parallelly run with me. If you have any doubts, you can share your screen and present, such that it will be done simultaneously. Otherwise, it will be like a one-sided presentation. Okay. So you just if you have AWS client, so it is fine. If you don't have, you can use this document. I can open and show you. If you have Linux, Mac, or Windows, whatever systems you are using, so you just for Linux case, you just have to run these 3 commands on your terminal, such that this AWS client will be installed on your system. Then you can download the data set using this command. Okay, so once you downloaded the data set, maybe in the next session we will do the classification task. Is it fine?
Yeah, that should be fine.
Okay, so if you have any doubt, you can ask, or else maybe end the session.
Yes. A question is about the papers for the final discussion. During the day, I think we will distribute the papers, and then you have to use this paper in order to get the discussion to the final session. So please pay attention to this issue also during the day and the next days. Okay.
Yeah. So as Professor Rufina have mentioned, so we actually by today night we will share some papers, and we will assign to all the participants only one paper. Okay. So in the validatory sessions, whoever have opted for grade, we will discuss with respect to that paper, and we will see that the way you are discussing, accordingly we will grade you for the whoever are opting for the grades for the GAN course, this course. Okay.
Okay, thank you.
Thank you.
Yeah, thank you.
We will meet tomorrow at 2.